to be able to introduce Alec Radford. Alec Radford is a research scientist at OpenAI. Alec has pioneered many of the latest advances in AI for natural language processing. You might be familiar already with GPT and GPT-2, which Alec led those efforts at OpenAI. And of course, earlier in the semester, we covered BCGAN, which was the first GAN incarnation that could start generating realistic looking images, and that was also led by Alec. So it's a real honor to have Alec with us today. And yeah, Alec, please take it away from here.
Yeah, totally. I'm super excited to be here and present because this course is like basically my favorite research topic on supervised learning. And yeah, just really excited to chat with you all today. So today I'm going to focus on the NLP and text side, and I'm just going to start a timer. And today I'll be talking about just kind of generally learning from text in a scalable, unsupervised kind of fashion, kind of give a history of the field and some of the main techniques and approaches, and kind of walk through the methods and kind of where we are today, as well as providing some commentary on kind of supervised learning versus unsupervised learning in NLP and why I think unsupervised methods are so important in this space. Yeah, so let's, I guess, get started. So learning from text, one of the, I think, prerequisites to kind of start with is standard supervised learning requires kind of, what we'd say is machine learning grade data. And what I mean by that is kind of your canonical machine learning data set is something, at least in an academic context, is something like you go use a crowd worker pipeline and you very carefully curate gold labeled standards for some data you're trying to annotate. And this is a pretty involved, expensive process. And you often are emphasizing kind of quality and specificity and preciseness to the thing you care about, the task you're trying to predict, and maybe a very specific targeted data distribution. And what this often means is you get a small amount of very high quality data. And even some of the largest efforts in this space, just because you have paid human feedback often involved, and sometimes you're ensembling predictions of 3, 5, or more labelers, it's often a few 100,000 examples is like a big data set, especially for NLP. In computer vision, you sometimes see things like ImageNet where they push that to 1 million or 10 million, but those are kind of the far outliers. And very many canonical NLP data sets might only have 5 or 10,000 labeled examples. So there's not really a lot of machine learning grade data out there, at least compared to what kind of the current learning complexities and efficiencies of current models are. One of the primary criticisms of modern supervised learning and deep learning in particular is how data intensive it is. So we really have to get that number down. And this lecture is basically going to be discussing all the variety of methods that have been developed for using natural language that kind of is available beyond kind of the machine learning grade data and unsupervised or scalable self-supervised methods for hoping to somehow pre-train, do some auxiliary objective or task, or hand design some method that allows you to improve performance once you flip the switch and go to a supervised learning on a standard machine learning grade data, or in the limit, as we'll talk later, get rid of the need entirely to have a classic supervised learning data set and potentially begin to learn tasks in a purely unsupervised way and evaluate them in a zero-shot setting. So there's a variety of methods. This lecture is going to focus primarily on autoregressive maximum likelihood language models. They're kind of the core, and I think they're the most common uniting thread that kind of carries the early days of this field through to kind of the current modern methods. But I want to make clear at the front that there's many proxy objectives and tasks that have been designed in natural language processing to somehow do something before the thing you care about in order to do better on the thing you care about. And there's quite a lot, and in particular in the last year or two, we've now seen that area really kind of grow dramatically. And in many cases, they now outperform the standard language model based methods that I kind of will use as the core of the presentation. And we'll talk more about the details of the differences as we get to those parts. So some more motivation and intro as we kind of go in. So I think one of the ways to think about this is like, what do we do with the internet? So, the wild internet appears and you can either have your glowing brain-esque representation on the left that we can laugh at, or we can make it, how messy and random and weird and difficult it might be for algorithms to learn from it on the right. So that's good old GeoCities. And so there's a lot of skepticism, I think, about kind of these approaches that might kind of at the highest level look kind of silly or kind of whimsical to be like, let's just throw an algorithm at the internet and see what comes out the other end. But I think that's actually kind of one of the like one sentence summaries of basically what modern NLP has been seeing a lot of success from. And I think one of the reasons why is just the internet is so big. There's so much data on it, and we're starting to see some very exciting methods of learning from this kind of messy, large-scale, and curated data. And so this is a great tweet from an NLP researcher, just kind of showing just how bizarrely big and kind of just massive the internet is, where you can go and find an article about how to open doors. And there's often a lot of arguments saying that, we're not going to, and it feels wrong in the limit to be like, yes, let's just throw algorithms at the internet and see what happens. Like that doesn't match human experience. That doesn't match kind of the grounded embodied agents that, we think of as, intelligent systems. And instead it's this kind of just like processing bits or abstract tokens. And so there's a lot of skepticism about this approach, but I think that just quantities of scale and other methods play very well with current techniques. And you see lots of arguments about things like, oh, there's this long tail, and we're never going to be able to deal with composition, and really, it's just maybe brute force can get us surprisingly far in the near term. Not saying that these methods or techniques are the end all be all, but at least today there's I think strong evidence that we shouldn't dismiss this somewhat silly approach at a high level. So let's start with kind of, I think, what would be the simplest starting point that we can convert from this kind of high level idea into something that looks like a machine learning algorithm. So we process a bunch of text on the internet, let's say, and we're going to build this matrix called the word co-occurrence matrix. And so what we can kind of think of is it's a square matrix where the ith, jth entry corresponds to, for a given word like water, the count of another word and whether they co-occur with each other. So it might be, you have to define what a co-occurrence is. So that just means that the two happen to be present together. And you might define a window of this. For instance, they both occur in the same sentence or within 5 words of each other, or in the limit, you can go quite far with like just happen to co-occur in the same document on the internet. And so you're just going to brute force kind of count this. It's just counting. That's all it is. We're just going over, tons and tons of text, and we're just building up this table, basically. It's just a lookup table, and it just tells you, oh, the words steam and water co-occur 250 times, or, the word steam is just in the data set 324 times total, or, the words hot and water, 19,540 times. So that's all we're doing. And this is a way, one, this is incredibly scalable. You can just run a Spark job over the entire internet with this kind of system and quickly get basically this giant table. And it's not computationally intensive. It's just counting and processing and tokenization. This thing can be run on a common desktop and get very far. And it's simple. It's just counting. So how good is counting a bunch of stuff? Like we're talking about something incredibly basic. It's just kind of how often do these two things occur together. And I think one of the big takeaways that I'm going to have a lot during this presentation is just how far these simple methods that are scalable and with large amounts of data can get. So this is a great example of a paper called Combining Retrieval, Statistics, and Inference to Answer Elementary Science Questions. It's from Clark et al., AI2 from 2016. And what they do is they take the same data structure, this word-word co-occurrence matrix, and they let me start with the task. So the task is elementary science questions. So it's just, I believe, through 5th grade, kind of, elementary school, kind of simple science questions. So they're multiple choice. They're 4, possible answers. And there are these kind of simple things like a student crumpled up a flat sheet of paper into a round ball. What property of the water changed? Hardness, color, mass, or shape? What property of a mirror makes it possible for a student to see an image in it? Is it volume, magnetism, reflectiveness, or connectivity? So this is the kind of thing that, again, is pretty basic in terms of like the high levels. They're, relatively simple facts, and they don't require all that much in the form of reasoning or comprehension. But they're still the kind of thing that we do give to, kids learning about the world. And so you might think that like, oh, this is the kind of thing where to understand a mirror, you really need to, exist in the world and to, learn about all these properties or to have a teacher. And how are we going to get there with just kind of this brute force thing that just counts a bunch of words and puts them into a table and then starts looking them up? And the takeaway here is that it can work surprisingly well. So you can't quite pass these examples. So the specific solver that we're going to use talking about in a second is the PMI solver, and that gets to about 60%. But random guess is 25%. So we basically almost have the error rate and get to a D with just this very dumb brute force approach. So what actually is this solver? They call it the pointwise mutual information solver. And what you can think of it as is it just scores all of these possible answers. So we have this sentence of context of the question, and then we have 4 possible answers. So what we do is we loop over basically the sentence, and we just look for the word-to-word co-occurrences, and we just keep counting them up. And we use this scoring formula, which is the log of a ratio between 2 probabilities. The P of xy is the joint, which is basically the co-occurrence. And so that gets you that count. That's basically looking it up directly from that table, the jth entry for xy. And then you normalize by this kind of baseline assumption, which is that the words should not co-occur more than by chance. So that would be just their independent probabilities multiplied together. As you can imagine, those may be quite small, and producting 2 together makes them even smaller. But some words co-occur together. So a mirror occurs with reflective, or electricity occurs with lightning, or crumpled up might co-occur with like hardness. And so that's all this method does, is it kind of just says these basic associations between words. And that can get you surprisingly far. It doesn't feel like real learning, maybe, and it's definitely not very human-like, but it's just an example of kind of the power of basic methods, and how something that doesn't involve any intelligence or hand waving that we might make about complicated systems. It's just a big lookup table, a Spark job that you might run on the internet, and it can get you surprisingly far. So there's a problem with working with these word-to-word co-occurrence matrices. They're huge. So let's say we have a 1,000,000 word vocabulary. So we have 1,000,000 words by 1,000,000 words, just to have the full dense version naively. And then you might store it with an int32. Hopefully you don't need an int64. So that's 4 bytes. So storing this whole matrix in memory in a dense representation is 4 terabytes. That's still huge for today. Most machines don't have that much memory in them. So, and if we were to kind of like start working with like, how do we use this system, or how do we kind of make it more general? We just have this matrix, and you can definitely design hand-coded algorithms to go look up entries and query on it, and we see that they can get quite far. But we'd like to do more, and how does this slot into NLP more broadly? So we want to come up with a more compact but faithful representation of the relations between the words and the information they represent. And we could just say that we really just want to find a way of re-representing this giant co-occurrence matrix as something more like what we know from deep learning and machine learning in general. So here's the algorithm called GLOVE from Pennington. I believe this is Stanford NLP in 2014. So we take that matrix of word-word co-occurrences. Like I mentioned, it's cheap, so you can run this thing over like 1 trillion tokens. And each entry xij would be the count of word I co-occurring in context with word j. And what we're going to do instead is we're going to learn an approximation of this full matrix. And the way we're going to do it is we're going to redefine a word as a low dimensional, or at least compared to a 1,000,000 by 1,000,000 matrix, much more low dimensional vector. So we're going to learn a dense distributed representation of a word. And all we're going to say is this very simple model, such that we're trying to predict the log prob or the log co-occurrence counts of the xij entry. And the way we're going to do it is we're going to look up the vector representation of word I and the vector representation of word j. And we're just going to say their dot product should be proportional to the log occurrence count. And that's all this is. And so it's really simple, and you can just use a weighted like squared error loss. So that's what this fxij is, basically a weighting function to account for the fact that some words are way more common, and you don't want to overtrain this thing on like those words. And you might also want to like clip, because you might have like extremely long-tailed frequency distributions and things like that. So, but at the end of the day, you just have wi dot product of wj, and you add some bias terms, and you're just trying to compare that to the log of the raw co-occurrence count. So this allows us to go from that giant m by m matrix, which might be a million by a million, to an m by n matrix where there's m words and each is an n-dimensional vector. And often this turns out that these can approximate that full co-occurrence matrix quite well, and they're much, much smaller dimensionality. So they might be just 300 dimensions. And there's a question of what does this thing learn and how does it approximate that? But empirically, it just can compress it quite well. And this might make sense because you can imagine that many words just never occur with each other all that often. And in fact, simple sparse storage of that full matrix can get a lot smaller already. But then we work mostly with dense distributed representations these days in deep learning. So we're going to smash it into the framework we know. So there's another variant of this.
Alec, quick question. So do you still have to first build the full matrix and then you run this? Or
so this is a way of having had the full matrix, you then run this as a way of kind of compressing or re-representing the matrix.
Got it. Thanks.
So now is an example where you don't have to build that full matrix. So there's another variant of a very similar kind of, and I think usually a more well-known version of kind of an algorithm in this class called word-to-vect. And so word-to-vect is instead a kind of predictive framework where instead of saying we've got this kind of abstract co-occurrence matrix, then we're going to try to compress it and re-represent it as word vectors. We're going to just work with natural sequence of text. So you might have a 5-word sentence like the cat sat on the mat. And what you're going to do is there's going to be a model that's trained to take a local context window, the cat sat, maybe 2 words of past context and 2 words of next context. We're going to do an incredibly simple linear operation like summing them. And then we're just going to try to predict that word in the center. So this is called the continuous bag of words representation. Continuous because it's a distributed representation. Bag of words because the operation that composes the context is just a sum or a bag. And then we just predict the output. And we can parameterize that as the log probability of the word in the center of the context. And there's the inverse version of this, which is the skip-gram model, which given a central word of context tries to predict the window. And so this uses kind of the more standard approach of online training, and it just streams over a bunch of examples of text. You can use mini batch training. It looks like your standard algorithms. Now, the same way I mentioned some tricks with using the log co-occurrence or a reweighting function, you need those same kind of things here. Again, many words span many different ranges of frequencies, where you might have words like the be literally 7% of all your data. So if you naively trained a word-to-vect algorithm without subsampling or resampling based on the frequency distribution, 7% of your compute's going to modeling the word the. And then some important word like New York City or something, or phrase, is just basically lost in the noise. So we use a reweighting function. I believe it's the inverse 5th root, so it just works. And that just heavily truncates the frequency distribution. So they're basically doing the same thing, though, at the end of the day. This is a predictive framework where it takes in a sequence and it tries to predict some subset of that sequence with a very simple linear model. And you just have the same word embedding table we talked about. But they both do about the same thing. And they're kind of the canonical first round of distributed or scalable, kind of unsupervised, self-supervised representations for NLP. Again, there's no human supervision classically involved in these algorithms. They just kind of have this automated procedure to just churn through large amounts of data. And word2vec came out of Google in 2013, and one of the first things they did is run it on a big CPU cluster with a very efficient C++ implementation and shove a bunch of words through it, and it works really well. And so let's kind of talk about what this does. So for this graph, I'm going to talk about.
Hey, Alec, can I interrupt for one moment? Can you go back?
Yep.
So on the left, it's the words are represented by vectors, and then you average, and you're supposed to get the vector representing the middle word. On the right, where do the embeddings live?
They're the same embeddings, WT. So they're both inputs and targets. So you would basically slice out some word, WT from your list. You would then also pull a sequence of context to be predicted, like the word before and the word after, and then you would have the same prediction objective, like the log prob of that word at that location. And there's other approximations that I kind of just am glossing over right now of how to do this efficiently, because computing a full normalization of the predictions over a full million size vocabulary is very expensive. So you can use a tree structure or a subsampling algorithm where you might normalize over only a randomly selected subset, and you can weight that subset and things like this. And
Is the
I'll talk a bit
prediction
about negative sampling in a little bit.
is the prediction some kind of inner product between WT and WT minus 2, or
Yeah, so that would be how you'd get the logit for the log probs. It's a dot
got
product
it?
as well. Yep, sorry, I should have
Thanks.
been clear about that operation. Thank you. Cool.
Thanks, Alec.
So yeah, what do we do with these things? So this is where kind of a lot of the first wave of kind of modern, modern's a contentious word, but kind of NLP starting to leverage large scale and supervised data started figuring out how to use these things. So these examples on the left are with Glove. And what we see is kind of a suite of tasks. So there's the Stanford Sentiment Tree Bank, which is predicting for a sentence of a movie review, is it a positive review that they like the movie, or is it a negative review that they didn't like the movie? IMDb is another sentiment analysis data set, but it's a paragraph of context. T-Rex 6 and 50 are classifying kind of types of questions, like who, what, where, when. And SNLI is a much fancier thing of logical entailment. So it's kind of measuring the relation between two sentences, a premise sentence and a hypothesis sentence. And you're basically trying to say, given the premise, does the following sentence follow logically from it, be entailed? Is it kind of irrelevant or containing information that's maybe correct but maybe not wrong, which would be a neutral? Or is it actually a contradiction of the previous sentence? So, it might be the first sentence is like, a woman is walking a dog, and then the second sentence is like a man is playing with a cat. And that would just be a contradiction of the first sentence. So that's SNLI, and it's a sentence level objective, and it's kind of this more complex operation because it's doing logical reasoning, supposedly, and it's doing it over semantic concepts. Like you might need to know the relations between playing an instrument, or that the saxophone is an instrument, so that if the premise is a man playing a saxophone, you need to know that the hypothesis might be entailing it if it's the man is playing a musical instrument. So that one has like kind of an interesting relation to some more semantic content. And the final example here is Squad, which is a question answering data set. So you get a paragraph from Wikipedia, and you have to predict, given a question, what the answer is from that paragraph. And so for all of these data sets, again, this is a pretty broad suite of tasks. You see multiple absolute percentage performance jumps from slotting in word vectors compared to randomly initialized components of the models that were used to predict. So you can always do random initialization, kind of the standard canonical thing in deep learning, or you could use these pre-trained vectors. And so they really do seem to help in terms of data efficiency. And you can see in some cases, like for question answering, that you can get a 10% plus absolute improvement here for Glove. Glove plus Cove is another thing, which we'll come to in a bit. And why might these be helping so much? So that's the kind of empirical data. Well, on the right here, we kind of have some of the work that Glove did to kind of inspect the properties of these word vectors. So they would, for instance, have a query vector like the word frog, and then they would show all of the different possible nearest words in terms of just cosine similarity to that first word. So you can see that immediately it's the plural version of it, frog to frogs. Toad is very similar to frog. Rana is like the, I guess, more scientific name. And then you get slightly farther out things like lizard. So you can see how that can simplify the problem space. If we have a distributed model and we have an input that's asking a question about a frog, if we don't have any knowledge of the structure of language or the relations between the word frog and toad, it's naive or basically impossible for that model to then potentially generalize to the same question asked about a toad instead. But if we have this dense distributed representation that is bringing together these words kind of into this similar feature space, then you might expect that, well, if the representation for frog is very similar to the representation for toad, the model might just be able to generalize and handle that. And there's even more relations and properties, which is beyond just similarity in that embedding space. You can also get very interesting relations, like the concept of like kind of like the CEO to a company might all be expressed in kind of the same subspace or the same direction in the embedding space, or connecting a zip code to its city. And you can see kind of how, how could this be happening? Well, co-occurrences kind of get you this, don't they? Honolulu, if you want to predict this random number, you've got to eventually figure out that, these do occur together because they are the zip code of one to the other. And so yeah, you get a lot of structure, even though, again, all we were doing, or one of the views of all of these algorithms are doing, is they're just processing very local relations in a very simple fashion. And it's just scalable and simple, but it can work quite well as a starting point. Now, these aren't the end of, obviously it's only 30 minutes into a 3-hour lecture, so there's a long way to go. So kind of, these are all cool and whatnot, and they really did drive the first few years of modern deep learning NLP and helping to move these models to much higher performance. But kind of what might be the issues with them? So, obviously language is a lot more than just the counts of words. It has a ton of structure on top of and in addition to words. And furthermore, context is very important. And these kind of fixed static representations of words that we're learning are just insufficient in many cases. So you might have, for instance, 3 different sentences. I went to the riverbank, I made a withdrawal from the bank, or I wouldn't bank on it. And all of them have the word bank being used in a very different context and, basically representing a different thing. Maybe it's a noun or a verb or, or just a phrase of expression. And so you really need to learn how to do more complex things. But if you're just counting whether 2 words happen to occur in a sentence, or in Word2Vect, kind of looking at a very short window and just using an averaging operator, you can't really model all that much complexity. So we need to do more. And there's also just kind of the design space. Right now you have this 1,000,000 by 300 dimensional matrix of like word vectors. And then the question is just, what do we do with that? And obviously we figured out quite a lot of ways to use them, but there's a lot that's still up to the practitioner. And this often involves a lot of task-specific models slapped on top of it. And that's where a lot of the first few years of research in NLP for deep learning went, was kind of designing all these task-specific models, a model for doing question answering, a model for doing summarization, a model for doing sentiment analysis. And they would all kind of take this common input of the word vectors and slot them in, but then there was a huge amount of design on top of that. And these models got progressively more and more complex with more and more details. And so you can kind of think this as like, well, we only really did the first step. Sure, learning word vectors is great, but they're really kind of like learning just the edge detectors in computer vision. And they get us something, but we know, like in deep learning for computer vision, there's a lot more that goes into a ComNet than just some edge detectors at the beginning of the system. And that's true for NLP as well. So there's a lot more going on in language beyond just these input representations. So kind of, how do we get there? Well, we're going to take a little bit of a detour into the history of language models and kind of walk through how this kind of method and kind of set of generative models kind of ended up providing one of the methods for moving beyond just word vectors and kind of introducing the second wave of modern NLP methods that use unsupervised or self-supervised methods. So fun overview real quickly is kind of 70 years of history here on one slide, where we kind of are looking at a language model. What is a language model? Well, it models language, and it's a generative model. So hopefully, depending on how nicely it's set up, we can draw samples from it to understand kind of what distribution it's actually learned and how well it's actually approximated the real distribution of language. So without getting into the details of how you sample, you can kind of see this kind of list here. So very early, there's this thing called a 3-gram model from Claude Shannon himself in the 1950s, and this kind of still makes basically gibberish. They also point to $99.6 billion from 204.063% of interest rates, stores as Mexico and Brazil, and market conditions. Well, that's basically gibberish, but notice that there's still a bit of like local correlation and structure. It says a lot of numbers, and then it mentions interest rates after 6.3% or 6.3%. And that's like all kind of right. And you can see how there's the tiniest bit of structure there beyond just like what it would look like if you just drew words independently according to their frequencies. And then there's been a lot of investment in this kind of field and area over the last few years. So Ilya Sutskever in 2011 kind of introduced a character RNN for the task. And so here, anytime there's a prompt, it's highlighted in yellow, which means it's a manually specified kind of prefix. And then you condition on that and you sample from that. So the meaning of life is the tradition of ancient human reproduction. That's almost a sentence. It is less favorable to the good boy for when to remove her bigger. So it clearly fell apart in the second part, but it almost got something there. And it's still gibberish, but it at least shows another hint of structure.
And then there's Rafal's paper from 2016, which is basically a much bigger word level version of that RNN from 2011, and just kind of uses scale and a lot more data. And here's a sample drawn from it. With even more new technologies coming onto the market quickly during the past 3 years, an increasing number of companies must now tackle the ever-changing and ever-changing environmental challenges online. So that's basically a sentence at this point. There's a weird thing where it repeats itself with ever-changing and ever-changing, but we've now got a phrase, multiple phrases or clauses and kind of longer-term structure there. So that's a big amount of progress. And again, as we talked about with word vectors, a lot of their failure is that they don't exploit context and they're kind of these isolated representations of only single words. So the fact that these language models were starting to learn context as you looked at and inspected their samples is kind of a clue that they're going in the right direction towards some of the functionality and behaviors we might want in natural language processing. So then the next major step came in 2017 and 2018 with the introduction of the transformer-based architecture. We'll talk a little bit about that later if that's appropriate. But it handles long-term dependencies much better through self-attention mechanisms. And then you start to see potentially multiple sentences that kind of flow together. And then the final one here is GPT-2, which can kind of take potentially a pretty low probability or difficult to understand prompt that probably isn't in the training data, like scientists discovering a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains, and they're able to speak English. And then it can write something that looks like a news article on top of that. This is cherry picked all hell like 20 times. I sat there until I got a good one. But it's progress, and most of these are cherry picked. So it's cherry picks against cherry picks all the way down. And yeah, at that point, you basically have something that just reads like a full news article, and it keeps characters and names persistent, and pulls information from the source sentence over multiple paragraphs. And this is all a lot of progress being driven in the last few years. So kind of now that we have just like, oh, look at the cool samples, let's like get into the details here. So this is going to be about statistical or probabilistic language modeling. And kind of the way we formulate this is we interpret language as a high dimensional discrete data distribution that we want to model. And kind of the setup, since this is a statistical method, is we're going to observe a bunch of strings of language. And the framing here with a probabilistic language model is we want to learn a function that can just compute the probability or density of new sentences. So we want to be able to compute, oh, what is the probability of the sentence, is it going to rain today? And we're just going to give it a bunch of strings, and somehow we're going to design a model that can compute this quantity. So what does it mean to compute the probability of a string? What should the probability of the sentence the cat sat on the mat be? Well, there's some people who kind of think that this might not be the most well-defined concept, or there's a lot of reason for skepticism potentially. Noam Chomsky in 1969 has a very famous quote, but it must be recognized that the notion of the probability of a sentence is an entirely useless one under any known interpretation of this term. So some people were quite skeptical. To be fair, this is well before kind of any of the modern Renaissance, and he goes on to kind of explain a bit more that there's quite likely that statistical methods can work. But it's a good example of kind of where we're coming from and some of the contrast in the field. So let's instead kind of like talk about why this concept might be useful. Like, why do we want to know what the probability of this is? And this is where I think it begins to see the connection between, what does a generative model do and how might we end up using it, or why might it actually learn useful functionality for downstream tasks or for transfer. And so, we could compare, for instance, the probability of the sentence the cat sat on the mat to the probability of the sentence the cat sats on the mat. And we would expect that, let's say we somehow have the true function here. We don't know how to learn it yet, but we just assume we have like the ground truth of the probabilities of these two sentences. Well, it should assign more probability to the grammatically correct one. And that gets you something like grammar. And that's, an important part of language is understanding its structure and what are the valid sentences or not. But, should the probability of the sentence the cat sats on the mat be 0? Well, no, because sometimes people fudge their keyboard or mistype. It should be much lower, but it shouldn't be all the way to 0, for instance. And then you can kind of get to more interesting sentences that you could query. You could say, what's the probability of the sentence the hyena sat on the mat? And compare that to the sentence the cat sat on the mat. And, we would say, well, as a human being asked this, you would say, well, hyenas, are wild animals. They don't often sit on mats unless they're at the zoo or something. So this kind of shows how to do this, to compute this probability correctly, you would need to start to have world knowledge. What is a common what is a common environment for a hyena? What does even sitting on a mat mean? And then you can ask other questions again. You could start to get to conditional probabilities too, depending on how you set up this generative model, is you might be able to query, given that the prefix is the substring 2 + 2 equals, what should the probability of the completion for be? It probably shouldn't be 1 because people sometimes joke that 2 + 2 = 5, but maybe if you had a bit more context, you would be able to disambiguate which of those two you might predict. And then finally, kind of coming back to some of the data sets or tasks we've already mentioned, if you have the prefix, that movie was terrible, I'd rate it 1 star out of 5, you really should know that that is a likely completion. And so to do that completion and to generate that sentence and to know that string is likely, you basically have to have that language model somehow have learned what sentiment analysis is and what is a likely relation between the concept of like 1 star or 5 stars and the kind of reception of the movie or the description of the movie before that. And so with that one, it kind of becomes clear that in the limit, these functions that these language models learn and compute should be quite useful. Traditionally, we approach that as a supervised learning problem, right? We were going to like, oh, let's go build a data set. Let's go collect, a bunch of crowd labelers and have them assign ratings to a bunch of different movie reviews. That's what the Stanford Sentiment Tree Bank is. But in the limit, this kind of unsupervised scalable method of just like fit a probability distribution to strings of language should eventually maybe be able to handle a test like this without any of the classic supervised learning framework being used. And yeah, so that kind of extends much more broadly. Those are kind of some, canonical example or some toy examples, but this actually can be quite useful. And this is kind of where language models got their start, in many cases 30 or 40 years ago, or 20 years ago in kind of machine learning. So they're often used for speech recognition and machine translation, which again are traditionally approached as supervised tasks with pairs of transcripts that are somehow aligned. And a major promise is that we can somehow leverage these language models to really help with these problems. And for speech recognition, for instance, you could prune the space of possible transcriptions from an acoustic model. There's a famous example from Jeffrey Hinton of how to tell the difference between the sentence recognize speech and recognize speech. They're very similar from a raw audio perspective, but if you have context, that these can be quite different things, and recognize speech is just also a much less likely string than to recognize speech. And for translation, for instance, you could re-rank possible translations based on a monolingual language model. So if you have an English to French translation system and you have some proposal of the French translation, you could say, well, hey, language model that I've trained already, how likely do you think this sentence is in French? And there's a lot of work on integrating this directly into decoders and using them as rescoring mechanisms. Old statistical language models really got their start often as in these tasks. So let's move towards actually having a computational model of language. So first, maybe we'll do some pre-processing, like lowercasing. So we'll take some maybe messed up text and turn it into just all lowercase to simplify it. We'll then, maybe set a vocabulary size to just like make the distribution easier to handle, to set it to like, a million tokens or something. So we might substitute a rare word like countertop with like an unknown token, just so we kind of don't have to deal with this like potentially open-ended probability of observing a new novel word never seen before. And then finally, we'll use something like a tokenizer, which will take a input string and return a sequence of tokens. So it'll chunk it into a sequence somehow with kind of some rules or logic. And this is another example of classic NLP work on designing tokenizers. So we might take the cat sat on the mat and chunk it into just the words and throw that punctuation on the end there. And then, because this is machine learning, we basically are re-representing these words as, unique identifiers or indices. And that's, again, a way to get a window into how a machine learning model really sees natural language. We come in as humans with so much understanding and context and from like lived experience, but if you try to train a naive supervised learning model and you start it from random initialization, it's a lot harder to understand what 23, 19, 24, 742, followed by 101, 23, et cetera, is. And I think this helps you get into the mindset of when people talk about machine learning models being spurious pattern matchers or just learning weird correlations that aren't true. If you looked at a bunch and like tried to do natural language processing tasks as a human, where your inputs were represented in this format, you'd probably be a lot worse than current machine learning models already are. And it'd be understandable if you made kind of mistakes as an algorithm trying to figure out how to make sense of any of this, especially once you get to some more complicated tasks like do these two sentences logically reason or follow each other. You could even just do a simpler thing like split into spaces. So there's a huge design space here, and I'm just providing a few examples right now. Okay, so there's character level, there's byte level, which would be kind of working on, if you just work on characters, how do you deal with non-ASCII text or text in a, like Roman numeral, or sorry, standard like lettering systems. So you could work on like a standard encoding scheme like UTF-8 byte stream. You could also work on Unicode symbols or code points. And then there's kind of these middle grounds between word level and character level, which would be something like byte pair encoding. And this one actually turns out to be super important. So I'm kind of just covering it as part of general NLP methods, and it's used by quite a lot of methods in the space now. So what this does, it starts with a character level vocabulary, and it kind of just merges the two most common pairs of characters at a time. So you might have T and H be the most common pair of words, characters, and then you'll combine them into a new token called TH, and you'll merge that and you'll resubstitute it in all of your words, and then you'll run this loop again. And so if you run this and kind of just keep merging and merging and merging, it learns basically a tree of merges that quickly pop out words, full words like the, and common endings like ing, and he and to. And this learns something that kind of lets us handle potentially the full distribution of language, while also having maybe the efficiency of representing semantic chunks like words instead of operating on these characters, which might result in strings that are 5 or 5 times longer, and require like much more compute and have much longer term dependencies that are difficult to handle than standard word models. So byte pair encoding from Rico Center is all over the place and is a very common middle ground to back off to character level if you see something rare you don't know, or to handle like all these different languages, while still having some sort of like kind of sensible handling of common words and frequencies.
Hey, Alec,
Yep.
Is there a common kind of number of byte pairs that you want to end up with? Because it sounds like you start with byte level, which is just 256 possibilities. And then you can imagine that you can have many, many byte pairs. And sometimes it goes beyond pairs, I think, right? Where you recombine an existing pair with just a byte, like the IN and the G. When do you stop?
So yeah, that's a great question. Usually you have a heuristic for merging only across or only within words. So you won't merge across like word boundaries with like white space or things like that. And that just helps with efficiency, because otherwise you'll start wasting merges on things like, common like pairs of, maybe filler words or stop words. And the other thing is you could just in the limit run this all the way out to a full vocab, but we often work on this kind of middle ground where, to get good coverage of natural language, you often need 100,000 plus words. And, in the limit, if you want to start having, common names and places, you need really like million-sized vocabularies. And that can just be incredibly computationally expensive. So you'll often stick this in a middle ground of like 32K BPs. And you're absolutely right that it'll merge all the way up to a full word. Like you will get things like, neurobiology in the limit that would be merged all the way with BPE just by doing merges over and over again. Yep.
Thank you.
Cool. So how do we compute the probability of a string? Well, the dumbest model is we could just assume a uniform like prior over tokens and assume all of them are independent. So we just product their independent probabilities together to compute for any arbitrary sequence. Dumbest model, but we'll start somewhere. All right, so let's get rid of some of these dumb assumptions. So we could suddenly like say, well, we know some words are more common than others. And that kind of word co-occurrence matrix has that diagonal term, which is just the frequencies or counts of words. So we could use that instead. And that would just allow us to say, well, the word these really common, so we're going to assign more probability mass to it. And the word supercalifragilisticexpialidocious is just pretty rare. So this would be called a unigram model, where all we do is we just product proportional to the probabilities of the tokens from like the empirical distribution. And again, we can estimate that just by counting a ton. We can then go a bit farther and start to exploit context. So again, we've talked before about how important context might be. And this is where you can start to see a language model begin to handle that potentially. So we could say instead of estimating just like the diagonal of that matrix, we can use that full matrix basically and say, well, given that we just saw the word the, how often is the word cat after the word the? And so we can kind of condition on that previous token and use a modified version of that like lookup or count table and start to handle a little bit of context. So that's a bigram model, bigram language model. But there's a problem of generalization here. And this is where kind of counting methods eventually like hit their limit. And yeah, we can brute force them with all of the data on the internet, but at the end of the day, they're not flexible enough. So let's say you've never seen a word before, like self-attention. You can't assign zero probability to that if you're trying to optimize for like log loss or something, because you just get an infinite loss. And if we just start going to longer and longer strings, this count method explodes, and the observances of every substring get rarer and rarer, and this just kind of hits a wall. So in the 80s and 90s, the way we kind of handled this is we kind of accepted that we couldn't handle the longer term dependencies here. And we kind of used clever smoothing methods of mixture models where you might put a lot of your probability on, the unigram or bigram or trigram model, which is more expressive, but you'll smear probability backing off if you don't see a word, for instance, or don't have a match to that unigram model or uniform model in the limit. And so this was kind of what you saw language models in the 80s and 90s spend a lot of their time on, is they kind of were they were still basically count tables and statistical count tables, but they optimized for kind of achieving something looking more like generalization of a simple form of kind of combining these mixture models. And so yeah, this is a good review paper if you ever want to kind of go back through the history of this and all the different methods developed there. You start to get things that look more like representation learning and even multi-layer models. So they'll start doing things like clustering over parts of speech or substituting for that. So it's a very hand-engineered way of potentially adding expressiveness, but it's a good history of kind of where these methods came from. So, since we're talking about NLP and language models as one of the core workhorses here, kind of how do you evaluate and interpret a language model? Well, probabilities are often within rounding error of 0, since language is a huge discrete space, and the sentence might, or a document might just be very long. And so the most common way of evaluating these models and saying how well does it do is we use a quantity that's not dependent on the length. So we use like the average negative log probability per token. And this token definition, again, might be arbitrary. It might be character level or it might be word level. And so if we're using character level, we might convert from base E to base 2 and report bits per character or bits per byte. You see a lot of common language modeling benchmarks work in this setting. And word level language models often exponentiate that quantity and report what they call the perplexity and set. So yeah, it's just giving you bigger numbers and better improvements because you're working on exp instead of log scale. So how do we ground these numbers? They're kind of abstract or random quantities. What is the difference between 1.23 bits per character and 1.2 bits per character, especially if you just spent 3 months of your life working on a paper and that's the number you got out. So, it's important to understand these quantities are data set dependent. It's really easy to guess all zeros. It's really hard to guess the archive. And, you can start calibrating the scales by saying, well, random guessing would get you, log 2 of 1 over 256, so 8 bits per character. And human estimates from, not the best studies, but they're the only ones we've got, have kind of tried to peg them, people in the range of like 0.6 to 1.3 bits per character. And the best models now are often a little bit lower than 1 bit per character. So that range probably is lower for humans. And we're somewhere, getting okay, but not matching humans on these kind of quantities. And, a way of grounding perplexities is again, use the same random baseline. So it ends up just matching the vocabulary size for like a standard model. So random guessing would be a perplexity of 50K. And one way of thinking about perplexity is as like a branching factor of language. So perplexity to the n is like the space of possible generations of length n, how many your model might assign. So you have a perplexity of 10 for a language model and you generate, a two word sequence. There might be 100 kind of high probability events in that space. And human level estimates, again, here are between 5 and 10. And an example, though, again, is this is always data set dependent and always problem dependent. If you have a lot of well-constrained context, like in translation, these numbers can be a lot lower. And best models are often like 3 perplexity on translation. So you're picking between maybe 3-ish possible likely words. And, that kind of agrees with like, maybe there's a few different ways for a human to translate 2 sentences, but it's not a huge space by any means. So evaluation type 2 is kind of what we talked about. So that evaluation type 1 is very much the generative model perspective of like, well, how good of a probabilistic model is this? And so type 2 is instead kind of transfer and the things we're really talking about and caring about more. There's a lot of ways we could use these language models. So you could say, how well does a better language model potentially improve the word error rate for your speech recognition system, or the BLUE score for your translation system, or the accuracy for your document classification? And this is kind of where NLP has really taken off, leveraging these language models. And kind of the history of the last 5 years has been discovering more and more ways we could use smarter and smarter language models, or better and better language models, to do more and more things. So let's go through kind of the history here. of kind of the sequence of developing real context models that can generalize better than these kind of count-based methods we've so far been kind of using it for all of our discussion. So the first one here is surprisingly, like honestly, this paper is amazing. If you go back and read it, it's from Yashar Bengio from 2003, and it has a ton of very modern things in it. It has skip connections like you see in things like ResNets in 2003. It's learning distributed representations of words, and this is kind of that core concept we mentioned right at the beginning of like representing a word by a vector with learned values for each location. This is like the paper that kind of really introduced this in a neural setting. And they were doing like large scale distributed asynchronous HDD on a cluster even back then in 2003. They had to do it because single CPUs were so slow. So this is like I think a 64 or 128 CPU cluster. And it would take them, I think, a month to train a model with like 3 layers and 60 hidden units. So this is it's still a n-gram model, but we're using a multi-layer perceptron to compute the kind of the conditioning on the context. So instead of this kind of count-based method, we have an MLP that looks at the index for word t-1, the index for word t-2, and t-, let's say it's just a 3-word context. So it sees 3 of these vectors concatenated together of the last 3 words seen. We then run it through a hidden layer, and then we feed it through a softmax to try to predict what the next word would be. So this is a trigram language model still, but we've changed the model from a count-based method to a distributed setting with a MLP. And this was kind of the first paper that heroically showed that they could match the performance of some of those super optimized n-gram models. But again, it took like 10 days or a month, and it was on a giant cluster. So neural language models really had some catch up to play compared to these smart, quick count methods. And this is a lot of what took this so long, was just, unfortunately, they do need a lot more compute. So then the next major step here was kind of moving away from these fixed context windows, which are kind of unsatisfying. We know that as humans, we can look back in pieces of text and condition on multiple sentences, but these kind of methods always so far have had fixed context windows and have only been able to process or condition on just the last few words. So this is kind of where RNNs come in, and Thomas Mikolov's 2010 paper is kind of the first modern deep learning version of this that kind of started working quite well. So we replaced that MLP with a recurrent neural network, and that allows for handling potentially unbounded context. Now it handles that context in a learned fashion, so you'll get an input word vector at one time step, and you'll have this context buffer, which is a learned memory state that the RNN kind of modifies and updates. And you'll use that to kind of represent a running summary of everything you've seen that's important for predicting the next potential word. So this has potentially unbounded context, but in practice, we'll train it with methods like truncated backprop, where we only update for and compute, how to modify the transition function of the state for up to like maybe 32 words or 64 words. So it might be biased in that way, but it's kind of just still can potentially learn to encode a lot of information into a learned memory system instead of kind of using like hard-coded methods of just like keeping the explicit input representations. So here we get, again, like probably one of the first real language models where on that previous one, we were still using a type 1 evaluation where we're just like, how well can it predict the next word? But here with Mikolov's paper, they showed that if you ran this for a speech translation system, you can get actually a much lower word error rate on, you not only predict better, and you start really improving over the traditional like n-gram based language models. But if you look at this word error rate table here, you actually see that it improves the speech recognition system. So your transcriber will make much, potentially like, over 1 to 2. So the KNN baseline here is 13.5% word error rate. So you mess up 30.5% of words. And using all these RNNs together, you could actually reduce that by over 2 points. And so you're talking about like a 20% error reduction, which is quite significant there. And this was like a lot of early language models were actually published in speech conferences because this was such a important and exciting application of them to start with. And again, you don't need to collect a bunch of speech transcription data here. In the limit, you could just run this thing over like New York Times articles and then use it to help potentially with your speech transcriber. And that's where a lot of the power comes in from an unsupervised scalable method and transfer capabilities. So we already showed samples from this one. but it's kind of a slightly different version where all these models so far have been operating on words and kind of having pre-built tokenizers to split it up and chunk it and kind of fix vocabularies. The exciting thing with character level models, so it's the same kind of architecture, a recurrent network. It approximates a richer transition function where you might have a different set of weights with multiplicative interactions. This was back when we thought optimization was hard, so it's using second order optimizers because RNNs are scary and we still haven't gotten used to like just first order methods working well. And it begins to handle much longer term dependencies. When you work on character level, you're suddenly talking about sequences that are 5 times longer. So you start having models that maybe handle hundreds of time steps, and that starts abstractly meaning maybe you could have a model that could actually parse a paragraph or parse a page. And it wasn't a lot better than Ngram models in terms of its perplexities, but it was very easy to sample from. And this was kind of one of the first, I think, demos that people might have seen online of a language model back on like some University of Toronto static website from like 2011. So the next major
Alec, quick question. When you look at character level models versus word level models, can you directly compare the perplexity?
If you're careful, yes. So, in the limit, these are both just predicting a sequence. And if you set it up correctly, you could just here would be the simplest way to do it with a character level model. Sorry, I should clarify. You can go one way. So you can compute for a character or a byte level model, the perplexities that it would assign to a word level model. But some word level models might have limitations, like using unknown tokens or out of vocabulary that mean they can't actually compute probabilities of arbitrary sentences. Whereas that's one of the expressive benefits of a character level model. So the simplest way to do this would be you would convert the word level model, like the token sequence it processed, like let's just say it's split on spaces. You'll just rejoin on spaces and then compute the probabilities the character level model assigns, and you'll have an adjustment factor. You could just sum the probabilities over the full sequence and then renormalize by the relevant metric. And we'll actually be using that later to talk about how to compare different language models more appropriately. But again, you need to have the expressivity to handle an arbitrary string to be able to compute this. And old models, because of compute limitations, often work with small vocabularies, so they wouldn't truly be computing the probability of arbitrary strings because they might normalize them in various ways.
Got it. Thank you.
Yep. So the next step is kind of going to multi-layer LSTMs and also introducing the LSTM again, even though it came out in 2000, it kind of got repopularized primarily by, or one of the major people to repopularize it was Alex Graves in kind of 2013-ish. So this is again a character level model, except we now have a gated RNN, which uses kind of these multiplicative gates and more complicated transition dynamics to better store state and to help compared to like a multiplicative RNN with kind of credit assignment and just trainability. And you start to get the things that like can handle kind of arbitrary streams of text. So you get something that's learning how to parse Wikipedia Markdown or XML. And Andre Karpathy kind of really popularized these models with like some blog posts in 2015 showing that they work for LaTeX, they work for XML, they work for Python programs. They're not generating valid things, but they kind of can handle this. They really have this flexibility of kind of feeling exciting from an unsupervised learning perspective. You give them some data distribution of like Python programs or something, and you just have it train over that, and then you get something that looks like it's really drawn from that distribution. So we kind of like talked now through like a lot of the early work here. And although there was one example with the Thomas Mikolov paper of actually having an application, a lot of this was kind of just like competing for competing's sake on type 1 evals, or like, look at the funny samples. So again, one of the very fascinating things about the last few years of NLP has been how we figured out how to really use these things much more broadly across the board. And this is where I think it really starts to get exciting. So one of the first papers to do this was the skip thought vectors paper from Jamie Quiros and collaborators in 2015. And so what they did is they proposed learning a RNN sequence encoder to provide context to a language model and basically to learn how to use a sentence level feature extractor. So what I mean by that is, let's say we have a sentence, I could see the cat on the steps. What this model is trying to do is it first ingests this context sentence in the middle. And they call it skip thought vectors because you could think of this as basically that skipgram model. That was, again, you take a word in the center and then you predict the word before and the word after. This is generalizing it to sentences. And it's using an RNN to kind of learn to summarize the context of the long sequence and to handle kind of predicting complex dependencies between multiple words. So we encode that center sentence with an RNN. We iterate over it in the left to right fashion. And then we have a language model that predicts the previous sentence, so what might have happened before this sentence, and then a language model that also predicts the suffix sentence that comes after it. And so what they then do is they say, well, a model that does this task very well should learn to kind of summarize this sentence in the middle. And for RNNs, it's still these distributed representations. So you have this state vector that's representing kind of in a learned fashion all of the previous words you've seen. So importantly, that's now generalized from representations of single words to representations of sequences that can exploit context and potentially handle more complex properties and disambiguate meanings of words. And they showed across the board that these models healthily outperformed classic methods like, so CBOW with word2vect would be the simplest version. So, what does a document, how do you represent a document with word2vect? Well, one of the feature representations you could take is to just average the embeddings of each of the words in the document. And that would be what this like CBOW baseline here is on a bunch of different data sets. And so you could instead say, well, we're gonna, we somehow learned this sequence extractor. We could run it, take its feature representation for each sentence and use that instead. And you kind of see that these models, if you use the combined skip of the like bidirectional models and using the forward and backward versions, you can actually get these to start to outperform the word2vect models kind of across the board. And it wasn't really like, this paper was kind of exciting, especially from the breadth of things they do. They have things like image captioning representations that they learn, and they kind of show, with analysis methods like TSNE that you see clustering according to classes. It was kind of like on the edge where it showed some pretty exciting promise, and it was, a lot stronger than potentially a CBOW baseline, but there were other still discriminative methods for like training models from scratch that were still matching it with like, well-designed comment architectures or things like this. So although this had like a very exciting kind of, it's a learned feature extractor that's able to handle long-term context and dependencies, it kind of worked, but it wasn't like sweeping the sodas away. And it was, exciting. And honestly, I think a lot of people ended up using it more as a language model where they saw some cool demos of having to generate multiple sentences. But it never really quite, blew everyone away from its quality. So this was like a good early hit, but it didn't quite, it wasn't a home run by any means. And so this is where Andrew Dai's paper from 2015, semi-supervised sequence learning, kind of comes at it from a slightly different angle. So again, for skip thought vectors, we just use this vector representation as an input to a model. And we fix the model itself, and we just like train another model on top of this vector representation. And it's a vector representation summarizing the whole sentence. So maybe that's kind of a difficult task to summarize all the complexities of long sentences, short sentences. So what Dai et al. Did instead was they said, we'll take this language model that we've learned and we're just going to fine tune it directly. We're not going to like pre-cache the features like kind of word2vect style. We're just going to take it, whatever parameters that language model learned predicting the sequence, we're going to use that as an initialization point for training a supervised model for a downstream task. And this is the one that started to get good results. And they were showing, compared to standard supervised learning on data sets with like 20,000 labeled examples and stuff like that, that these models could get quite far. And so you see in the limit that if you kind of have all of your different baselines here of word vectors feeding as inputs, but then we could use like a sequence autoencoder or a sequence language model and fine tune that, and you start getting quite large drops here. And what's kind of cool here is these two different rows here. One of these is pre-training only on the IMDb movie reviews, so basically the same data set. It's a two-stage algorithm. And then this third table here, or this third row here, is using a bunch of unlabeled Amazon reviews. And that's starting to get towards transfer learning, starting to get towards, well, we can run this thing over a lot of data. And as we get more compute, we can just add more data from the internet. We can feed in more, and we see that that actually improves things significantly over only using like the small standard supervised learning data set in isolation. Some of this might have just been at the time that it was difficult to train language models and train RNNs back in the day. But as we'll see through the rest of this lecture, the methods have kind of continued to hold on top of this and continue to make progress. So this is the first one where it got a strong SOTA, and there were strong baselines before it, and people started like really. I mean, well, to be fair, it came out and not much work happened in the space for the next 2 years. But it kind of, and a lot of that was because it like really just killed it on these sentiment analysis data sets and not as much elsewhere. And this really took some further work to kind of figure out how do we make this a generalizable approach that works kind of everywhere the same way that like plugging in word vectors does. So moving back one moment to a type 1 eval, there was a follow-up paper in the next year that kind of really started to push on scale and compute used for training language models. As we mentioned before, they've kind of always been compute limited. So this was that Google paper that showed kind of the first language model that could generate something like a coherent sentence. And a lot of it was using a larger data set. So the billion-word benchmark was a big data set at the time. And they use an 8K hidden unit projection LSTM, which uses basically a low rank factorization of like the transition hidden to hidden transition matrix just to keep the parameter count down while keeping the state size high. It's character aware with some improvements that let it process the character level inputs. So you kind of see on the right that this is starting to get to be a kind of complex system. And then they throw a large vocabulary. They throw 32 K40s at it, so 32 GPUs for 3 weeks. And they kind of really got a huge improvement over the previous results. And at this point, those old n-gram language models, the old statistical methods, were in the mid 40s or even in the 50s and 60s, were hybrid systems. And suddenly you're at like 23.7. So you basically have this metric. Again, it's exponentiated, so it's actually like a 20% reduction in like just actual log loss. But you're starting to see a lot of significant progress in this space, just throwing scale at it. And this ended up being, something that was really developed just to push it and say, how far can we get, sentence quality? Can we start to get something that looks like coherence? And one of the surprising results is it turned out that this actually paved the way for further methods. Even though it was just designed to be a really good language model and just better predict the next word, it ends up laying the foundations for a paper we'll talk about in a little bit called Elmo that really was the first one to crack how do we use these LMs all over the place and start seeing it working for question answering and summarization and all of these different domains. So there's kind of a bit of a tidbit here. We're at an hour. Should we stop for a little bit, or let me check if I have a stopping point? I'm going to go a bit farther. We could go to about 1:30 and stop for a little bit longer there as my kind of current guess.
Yeah.
Okay, cool. So, I've motivated scale a little bit. So like I mentioned, there's a whole internet out there. There's so much information, and that perfect language model would, basically from one view need to fit the internet into its parameters. Given how big it is, it's not surprising that we're going to need a big model to do that. We're going to need a lot of compute potentially to do it, to get as close as possible. And for many of these tasks we're talking about where we want to learn long-term dependencies, we want to learn complicated tasks, they might be quite rare. They also are quite difficult. So, the closer you get, the better you are to maybe learning real interesting behaviors versus kind of a basic system that just like is locally plugging a few words together. So another, just vivid way of pointing this out is a small character RNN is basically gibberish. This is what happens, this can be a very good architecture, but if you don't give it capacity, it just can't really learn language. There's so many words, there's so many objects, there's so many relations. You really need a lot of expressivity to handle all that complexity. And another way of pointing this out is classic resources that were built by humans trying to map out kind of like the relations between all words in natural language, build hierarchies over them. So there's really heroic efforts here like WordNet. They were larger than many of the language models we were still training, especially a few years ago. So it might have like 5.5 million relational features in this package. And when you have it zipped on disk or unzipped on disk, it's like already 55 megabytes. And a lot of common language models, especially early on, were only a few megabytes of parameters. And so we know that this is probably going to be very inefficient. And we're probably going to need quite large models. And right now, the answer we have so far is to kind of address this fact with scale. And hopefully we do find out more efficient systems, and we'll talk a bit about that later too. But right now, kind of the first dumb thing we try is brute force it with scale. And another reason why this is worth investing in is it's now a very well validated empirical trend. So across the bottom here is for both language modeling and for like computer vision, kind of the performance of models laid out on log scale plots, where you have log scale x-axis, which might be the amount of words you train on. So every new tick is a doubling of the data set size. Log scale is not great because it quickly gets inefficient, but these trends are incredibly linear. They're very predictable. So like it's almost like the natural kind of domain to think about is like, how does this look on a log scale? And you see that again for language models on the left, and for like the performance of like captioning image classification systems on ImageNet in the middle. So these are quite consistent trends, and they span now quite a few orders of magnitude. So far they've continued to improve from 6 million parameters up to 600 million on like ImageNet, and data set sizes spanning that's probably over two orders of magnitude there, or 2 orders of magnitude there. And also compute is becoming available as investment of more resources in machine learning and AI, and improvements in hardware and distributed training have kind of allowed for, even though there's this logarithmic or this heavy demand for additional compute to see kind of finite sized improvements, at least as of yet, kind of the industry as a whole has been developing techniques and systems to keep providing that additional compute to keep these trend lines going. So that was kind of just a quick digression on like why scale might be important, and it really intimately plays into like where these language models came from and how they kind of had their success. So here's a kind of a cute example looking at kind of starting to get away from just learning these kind of feature representations that could then be reused by downstream tasks towards maybe we can learn the tasks themselves without having to have standard human labeled feedback, and kind of share that intuition with like the talking about the computing the probability of the string. I rate this 1 star out of 5 after seeing the prefix of the product review. So this is a paper I did in 2017, which was like kind of a very targeted experiment here. And one of the hypotheses I was working on was that maybe just data was the bottleneck. Our models are so inefficient that if we were able to just tile kind of in an unsupervised fashion the landscape of one domain we might care about, like product reviews, we could maybe do quite well. So we made a much larger data set at that time, or rather we reused an existing data set from I think UCSD and Amazon in partnership, which had 40 gigabytes of text. So that was way bigger than that billion word benchmark. And it's all in just one domain. And we trained a byte level language model on this for a reasonable amount of compute a month on 4 Titan X's. The model ended up underfitting a lot. But one of the most interesting things about this is if we go and poke into that model and say, well, you have this hidden state that summarizes everything you've seen, and we do probes over that, we found that actually there was a single unit within this language model which very vividly and directly just computes a running estimate of what is the sentiment of the characters I've seen so far in the review. So you can see that, as it turns on, this is one of Michael Crichton's best books. And so we have green colored as positive and red colored as negative. So again, there's no supervised learning going on here. This is all just unsupervised prediction of a byte stream. It just sees a stream of bytes, 40 billion in a row, and they're all just numbers 0 to 256. And it somehow figures out, in order to better predict this text, it uncovers this useful feature, which is, well, is this review going to be excited or dismissive? And it can handle complexity where it can switch from a great start to something where it's like here in the middle, seriously, the screenplay and the directing were horrendous, and then it suddenly drops off in its performance analysis and starts going negative. I can't fault the actors. I know good novels especially are hard, but this may be the absolute worst disparity in quality between a novel and screen adaptation forever. So it really does it. And it turns out that if we just threshold on this unit, so we're not even fitting parameters, we're fitting one parameter, it actually was matching these old word-to-vect or bigram baselines and even things like skip thought vectors. And it's just a single unit in the model, and we're just running it over the document and thresholding the value at 0. And so this is a histogram for positive reviews and negative reviews of what this system does. So this is kind of showing, I think, in a very clean and pure way, how you can really do some unsupervised representation learning here and start to learn something that really helps potentially with downstream tasks. It's very hand engineered. It was very targeted. We knew that product review sentiment is a very important feature. So we were kind of really hoping that something like this would happen and it would learn a really good representation. But it was, it's still kind of shows a proof point when with limited scale, but lots of data, you can get something done here. A follow-up work we did with Scott Gray was pushing on kind of model size again. So we said maybe hidden state size is the bottleneck. So again, these standard LSTMs and RNNs summarize the entire past context as a fixed length feature vector. And so that might be for a standard model and a big model, like 4,096 units, or that Rafal's model was 8K units. And, if we had like 300-dimensional word vectors, if you naively just concatenated them into that state representation, you could only handle like 30 in a row with like an 8K or 9K state size. And that's only about a sentence or two. So we thought that, maybe it just turned out that models were really limited by their state size. And so we pushed on these kind of block sparse methods that kind of allowed us to train with much larger state sizes, that we would factorize the weight matrices such that they would be represented kind of as this two-layered system of having a dense block and a lot of sparse blocks that are pruned away. And we saw that these were slightly more efficient in terms of parameters, and they also worked better on things like sentiment analysis when evaluated by these linear models, which is like a standard probing for how good of a feature representation have I learned. And that's partially because linear models just like lots of features, and that's all where their expressiveness comes from. Linear separability is easier in high-dimensional spaces. And yeah, this was kind of like explaining some of the history of us pushing on trying to get these things to work and figure out how to like really, push their performance potentially. And so this is like showing again that that performance analysis of these units learned by these models. So this is how that kind of representation evolves, and we show kind of data efficiency on the x-axis here. So in the limit, we know there's that zero-shot performance of fitting a threshold to 0 examples, and that actually turned out to be about here on this graph if you used all the data to probe and find it. But if you just fit kind of naively, as you saw more and more data, you could start with, like in the limit, only needing 10 labeled examples to beat some of the original supervised learning baselines, which just train systems from scratch. There's this recurrent neural tensor network paper from Searcher et al., very early deep learning work here, with a really cool complex model. And we were able to match it with just 10 labeled examples, whereas it was trained on all 8,000 in this case. And then as we kind of keep adding more and more data, we see that the representations learned by these language models can be quite powerful. And you're kind of able to like quickly sweep through kind of in the limit, if you don't have any pre-training, you started getting into these increasingly complex and desperate's maybe a judgy word, ensembles of 30 different models to hit SOTAs. And then we're able to just use this model that exploits this unsupervised learning on a lot more data to push significantly higher. And then that small world improvement with block sparse had another large jump above that. And so this is kind of one of the precursors that, or kind of heralds what's about to happen on every task over the next few years. This is 2017 as like this field really starts taking off. So we mentioned this kind of cool and interesting thing of learning a single feature within one of these networks that kind of really shows some representation learning going on. And so there's another really great paper I love here from Roy Schwartz and collaborators in 2017 that I think, again, starts to speak to, hey, these language models that are recurrent networks or more expressive neural networks are really actually learning something interesting and beginning to be useful for downstream tasks that might be difficult. So this is a data set called the story close task. So what you do is you have a paragraph of context. In this case, Karen was assigned a roommate for her first year in college. They go to a music show together and it goes really well. And then you're trying to train a system to predict which is the right ending and which is the wrong ending. And so this fits very cleanly, or this is what Roy was quite clever about, was realizing that this fits very cleanly into the generative modeling framework. You could say, well, what is the probability of the right ending versus what is the probability of the wrong ending? And again, as we get better language models, they should start to learn to exploit context and assign the correct probabilities to these different strings. And so very early work kind of took the classic supervised learning approach of just throwing, a model maybe with even word vectors pre-trained at the system and treating it as like a binary classification task. But in this case, this story close task, it's difficult to generate this data. They only had 2,000 labeled examples. So a purely supervised discriminatory system really couldn't get that far. And they actually were basically not performing much better than random. And so what Roy was able to show was that, well, if you exploit tons more additional data, which was available of like training on small short stories, and then you use this model to score the endings, so it just produces a single scalar, which is like the ratio of the probabilities. It's the same PMI trick that we talked about before, but computed for a language model, where you say, well, what is the probability of the ending given the story? And you normalize by the probability of the ending in isolation. And this trick just helps a bit compared to just computing only the probability of the ending given the story. That actually still works quite well, but you get a fair amount more. And so they were able to significantly improve the performance on this data set. Again, in the limit, just using that single feature, the RNN-LM features here, they got a almost 10% jump in performance just by using the generative model off the shelf. There's no discriminative training. It's not exploiting spurious correlations here because it doesn't see any labels. It's just fitting a threshold of what it already thinks is the right ending versus the wrong ending. Another quick interlude of scaling. So these kind of all are happening messily together. And I think this gives kind of a sense of how, research fields often involve, where you see these different authors and different people pushing down different lines of work, and then kind of things come together in exciting ways. So this is work from Noam Shazir, really just pushing on maybe parameter count as the bottleneck. Maybe that's what's been holding back language models. And so they really went crazy here. And they train models that have these what they call sparsely gated mixture of experts layers. So you have your standard LSTMs in pink on top and bottom of this model. And then in the middle, you sandwich in what's called this mixture of experts layer. And what this has is it has a gating network that decides to pick basically a 2-layer fully connected network. And it says which ones should slot in for this given word. So you can think that, maybe you want to memorize a lot of information. And when you see, they went to the city blank or something, the mixture network and the gating network will say, oh, I should load up like, the expert that handles, where cities are in the world, or this is kind of just a hand-wavy high-level intuition. And particularly when you train this thing at large scale, because it's sparse, only one expert's being evaluated for any given location at a time. So you can group these, and you can have many of these experts being trained in parallel. And so they're able to push to like, an eye-popping 137 billion parameters in this language model. It's all in this very specific submodule, but it ends up being more compute efficient, and it has like a lot of clever and very impressive system engineering work to handle how do you run this thing at scale and not have it be efficient when handling so many parameters there. So now we come back to type 2 evals and kind of the standard slotted in and see how it does. And this is like really the paper that kind of set this field off. It's called ELMO from Peters et al. This is AI2 work again. ELMO is the name of the model, but it's really about deep contextualized word representations. And this is kind of where there's the clean mark between the word to vec error and the language model error. And so the way they do this is they kind of cleverly say, well, what do word vectors do? They slot in kind of as inputs, and they re-represent, this discrete identity or ID identifier token of like, word, cat being ID 256 with a distributed representation. And as we discussed before, things like context are missing in this case. So this paper talks about how to use a language model to do the same thing. They're substituting the input representation, but instead what they're using is a deep bidirectional language model. So this is kind of the schematic here, where they have a forward LSTM that will first take in its own learned word representations, and it'll iterate over the sentence in a left-right fashion. And then they want to, have context, not just for sentence words that happened in the past, but words that might be about to happen. So they also run a backwards LSTM in the other direction from the right to the left. And then they have this be a hierarchical, a deep model with multiple layers. So they run 2 layers of LSTM. And then what they do is they learn weighted averages of the word vectors. So maybe for some low-level task, you only want those input representations. But maybe for some tasks, you really want that kind of long-range context. And so you might want to use the higher-level layers. And so then they re-represent, instead of feeding in those kind of like one-to-one look up in a table what the word vector is, they have this RNN language model that processes the sentence or piece of text in both directions. And it learns to reuse its hidden state representation as the input to the model instead of the word vector representation. So kind of seeing all those earlier results like skip thought vectors showing that, well, you could learn a distributed representation of a sentence. This one does it, but it does it at a word level. And it just cleanly slots in where word vectors used to go. And so what this is quite nice by is it allows you to have very direct comparisons with prior work. And across the board, they basically show that like simple baseline models, which substituted to use these representations instead of word vector representations, were outperforming very well engineered, very tuned state-of-the-art systems that were like squeezing as much performance as they could out of word vectors. And they're getting, quite large numbers here where you see 10, 20% relative error improvements. And importantly, they kind of have that clean sweep of very many different tasks like question answering, entailment, co-reference, NER. So even classical tests like part of speech recognition and the like. And this kind of really just swept everything, and it was very clean. It kind of like made clear that, okay, word vectors were great, but it's time to, here comes the new thing. And the other very important and fascinating thing I find about this is this model was that language model that was developed or the language model they use for this system is that language model that Rafal developed in 2016 at Google to just, along with co-authors like Oriol Vinyals, that they really were just pushing on perplexity. They were just pushing on how well can we get a generative model to predict this text. And then, 2 years later, 2 years later, someone just was like, wait a second, this thing's learning amazing representations. And, those two works are separated by 2 years in completely different research labs. And they just discovered that, these language models are really doing something here. Yeah, so that's kind of like really where things turned. And you see, again, looking at data efficiency, that when you're at very low amounts of data, you get huge improvements, like 10+% absolute improvements. So that really feels like, as you get more and more supervised data, you can begin to overcome the limitations of training from scratch. But in the limit, you want to use as little data as possible. You want to learn as quickly as possible. So this is like very exciting. And it's kind of like really got everyone to start stirring and paying attention to this field. Yeah. So final one before the break is kind of, you could think of it as pretty much in the same vein as Elmo. And what we did instead is we took a better language model again. So transformers came out, and we were really excited by their ability to handle longer range dependencies. And they were also very compute efficient, so you could train them quite well and quite fast. So we swap out the recurrent network, or the LSTM, in a language model for a transformer-based language model. And if we want, we could talk a bit about self-attention and transformer-based architectures in a bit. But now just think of it as like we subbed in a different, better architecture. It's slightly larger. We use a similar data set of books. It's the same data set that skip thought vectors introduced / trained on. And we just fine-tune it the same way that Andrew Dye et al. Did. And this exciting thing here is we saw that we no longer needed these task-specific architectures for each task. So, a lot of the cleanliness of Elmo was that because it was just substituting the input representation, you could reuse all of those hand-engineered architectures. And often they would, counteract for the issues of handling long-term dependencies in RNN with like an attention layer or the like. But they still require, that engineering of each of these tasks for each of these different architectures, which means that you're still leaving performance on the headroom. It's now like we're initializing the mid-layer features of a CNN instead of just like the edge detectors of the lower layers. But then we still are sticking new layers on top. So we were trying to like really kind of move towards a general purpose framework that kind of allowed us to reuse the same architecture everywhere and not have to have as much of this task-specific engineering, which requires a lot of effort and time and grad student hours to like push those systems forward. So we have this transformer-based language model, and we kind of showed that for a fair variety of tasks, primarily classification, we kind of take the same model, and without having to modify it or introduce new layers, we could just fine-tune it with only a linear classifier tacked on top, and we could, across the board, do quite well. And in many cases, we were outperforming ensembles the same way that Elmo was doing before, and using basically the same unified architecture to perform quite a lot of different tasks. And the GLUE benchmark had recently come out as like kind of a standard multitask benchmark. And this was kind of one of the first major ones to bump up accuracy there and reduce the complexity of it. And there's two particular things that I'd like to focus on for discussing some of the results from that paper, which is if we ablate the number of features transferred, we really see that this is a 12 self-attention block model. We really see that you need all those layers, and the random initialization of higher layers was not working well at the time. It may be, as always, that you figure out better initialization methods and you can close that gap. But you see kind of cleanly that we're transferring a deep, a deep distributed representation, and the deeper it was, the better it was generalizing, and that seemed to hold true across multiple data sets and was a very clean kind of performance increase as you just transfer more and more of those blocks. So Elmo was a 2-layer model, and now we're going to like a 12-layer model. And then this rightmost graph is really the one that I want to focus on, and this kind of links together some of the hints and pieces we've been seeing so far through like many of the different papers, which is kind of this interesting behavior of sometimes the language model is learning a supervised task or a task we kind of thought needed supervision to classically train in the machine learning framework without any direct explicit labeling or supervision of it. So what we did here is we took this transformer language model and we kind of designed these heuristic ways of having it compute probabilities the same way that like Roy Schwartz was doing. And we kind of started to extend that beyond just the very specific thing, like which of these 2 sentences is most likely. So like, for instance, we could take a language model and do exactly that example at the beginning and ask it, well, you just saw a movie sentence review. Do you think the word very positive or very negative is more likely after seeing this sentence? So this would be this probe here, which is sentiment analysis in blue. And so we show over the course of training this language model, we evaluate this kind of zero-shot performance probe. And we call it zero-shot because, and this is a broader, we didn't invent zero-shot by any means, but it just means evaluating on a task or a data set or a class that we've never seen before, and we haven't done standard supervised learning to update the representations or to train the model to do this. And so we see that kind of as you train, you steadily improve performance. We've normalized task performance so that 0 is random guessing and 1 was the overall state of the art. So you still see across the board that these models are, nowhere near SOTA, and often they're less than 50% of between SOTA and random guessing. But they're showing clear and steady improvements, and they're showing that even on tasks like question answering. You could actually, take a paragraph of like a question answering task and ask it, well, which of these answers do you think is more likely? And there's no supervised training here. It was trained to predict books, and then you ask it like a 5th grade science question, and it starts to, sorry, I shouldn't anthropomorphize it so much, but you just probe it, you compute some conditional probabilities from it, and you start to see progress being made on, some potentially quite far afield tasks. The final point to make here too is self-attention and transformers really seem to help a lot here. Whereas we did the same exact model or, equivalent size and similar compute with an LSTM. And we were seeing that, especially on these zero-shot tasks, sometimes it could do relatively well, but on some of them, especially ones that handle long-range dependencies, you really need these self-attention layers to handle long-term dependencies. Cool. So I think we're at about half time for the lecture, and I think that's probably a good time for a break then.
This is fantastic, Alec. Thank you. Let's take a break till 6:50 Pacific time. So well, about 8 minutes. Does that sound good?
Yeah.
Okay, great. And I'll pause the recording for a moment here.
Sure.
Can I ask a quick question first?
Mm-hmm.
Yeah. If you have a certain limitations on how large a model you can train, like for example, if you need it to run on like a particular device, and you can't like train a large model or like fine tune off an existing one, are there any strategies?
Yeah, I mean, so I admittedly have been emphasizing the need for scale, but it's kind of a continuous spectrum thing. And there's some work we'll be talking about later that kind of focuses on efficiency and kind of how far you can push models of a given capacity and size. Probably the answer here, I think from a pragmatic perspective, is to kind of use whatever's the largest thing you can fit into the given device framework or resource specifications you have, but then kind of really pushing on how far you can take that thing. And some of the methods and techniques that have been developed, especially in the last year or two, have kind of increased efficiencies by factors of maybe 5 to 10. So there's, I think, a lot of promise there from really pushing even with a fixed size. And many of those still fit on single GPUs. Yeah.
Thanks.
Cool. Yeah. So yeah, I guess given it seems like the class has gone over transformers a few times, I won't do the super detailed version here. So yeah, I guess we'll just kind of blow through that real quickly. So we've kind of talked right now so far about mostly standard language models and kind of using different architectures, character level RNNs into LSTM, word level LSTMs into transformer-based language models. And they're always kind of trained with the standard autoregressive left-right, or in the case of Elmo, adding a backwards right-left language model. And that's nice. It's a clear framework. It allows you to compute probabilities easily. It allows you to sample kind of in just a iterated fashion. It's not the fastest, but it's quite simple to do. You just feed in you sample from the distribution over the next word, and then you feed that in as a new input and condition on it, and then resample. And so it's a very clean and like general framework, but it may actually not be all that optimal. So it's cool and exciting to see some of the things that these language models are doing. And some of the work, as I was just mentioning, has really pushed farther by walking away from that very explicit like left-right autoregressive language modeling strategy. So this is a common leaderboard. It's called the Glue benchmark, and it combines a set of like 9 tasks together. And this was pretty important for the field to kind of standardize on the set of tasks people reported on. As you can imagine, especially early on when the research is kind of scattered and not all that standardized, you kind of see people picking their favorite benchmarks. I was totally guilty of this myself. I really cared about sentiment classification just because I happened to find that to be an interesting task and worked on it a lot. And so my papers would report on sentiment classification, and then someone else's would report on entailment, and someone else would report on question answering. So you kind of had this lack of commonality and comparison points. So the Glue benchmark came in and said, we're going to standardize.
We're going to focus on sentence level comparison tasks primarily, and we're going to kind of have a suite of them. And we're basically going to say, hey, you should report on all of them, so you can't hide your bad results on one. And this helped drive a lot of progress too. So this is a screenshot of kind of where this leaderboard has gone, showing all of these new improvements and methods. So there's the by LSTM Elmo baseline at the bottom that we mentioned, and GPT-1 would have slotted in slightly above that. But then there's BERT at now ranked 20 from Jacob Devlin and crew. And then there's Facebook AI's Roberta as another big jump. And so we saw it like on the average metric here, which kind of just averages the performance across all these different tasks. It went from 70 to 80 between the by LSTM Elmo baseline to BERT. So that was a big jump there. And then an almost equally sized jump happened with BERT to Roberta, which we'll talk about in a bit. And then there's newer things like Electra and T5. So this kind of whole area has really, really exploded in the last year, 2 years in terms of the amount of teams, and basically every major research lab, Microsoft, like Stanford, NYU, like pretty much, AI2, you see a huge amount of people, Baidu, everyone everywhere has been kind of pushing what they can do on this, this kind of benchmark, and really seen a lot of progress. So we're going to go through kind of each of some of these improvements. That these are highlighted select a few. There's many others, so sorry if I cropped your briefly was a cool recordings back on. So an SSD2 is like sentiment analysis, like we mentioned before. So it's kind of a, again, a diverse suite of tasks here. So how do we kind of, what are these big improvements we're seeing beyond the standard left-right language models? And there's one more point to make, which is there is a human baseline here, and it's slotted in actually in the middle. It's in 12th place now. So what does it mean? Like, are these models actually better than people? And the answer really is no, and it's complicated and confusing, and we'll chat about this a bit more later. And supervised learning is always playing tricks on you. But now these models are like really, went from like in the last 2 to 3 years because of leveraging unsupervised pre-training and like kind of these scalable methods to really make quite a lot of progress in this space very quickly. So this is BERT. So what BERT does is it basically finds a very great way to hybridize a language model objective with kind of the importance of like bidirectionality. So again, by default, we have this like left-right autoregressive factorization where we say, given the previous words, predict the next word in the language model. And that's like what GPT-1 does. And so what we see with that is you're not able to exploit context from the right. You're not able to see, by masking the model, you have to prevent it from being able to just look at the next word and say, well, I see in my sequence that it's cat, so I'll just learn to copy it over and predict cat. So that has a major limitation. And when we released GPT-1, we actually weren't able to do well on, or we found that some of the question answering data sets we just couldn't do as well on because we weren't able to exploit bidirectional context. Whereas Elmo was the old bidirectional language model, and with an LSTM, and because they train a forward one and their backward one, and then the average of the representations, that works quite well for shallow models, and that gets you that bidirectional context, and that can help a ton. And they performed us, still outperformed us on some data sets because of that. And then BERT basically figures out how to have bidirectional context within a self-attention model, and the way they do this is they change the objective. So they're no longer doing this like standard, maximum likelihood training on like just the data distribution. They use this kind of proxy task called masked language modeling. So again, at the bottom here, we can see left, right, LM is like the cat sat on the, and then you blink out a word and it's supposed to predict mat. Right language modeling would be, we'd go the other way around and say mat, the, on, sat, cat, mask, and predict, the there. And so what masked LM does is it just takes your input sequence and it corrupts a few locations, 15% in the case of BERT, and it trains the model to predict what's at those masked locations. So, it might, in this case, there's no like left requirement or right requirement. It just randomly selects 15%. And this allows you to have bidirectional like representations. You can't leak the word because it's masked in the inputs. Whereas for a standard left-right or right-left LM, you kind of hide that. This is probably one detail of self-attention models that you have the self-attention matrix, and that kind of defines the connectivity pattern between different locations in your sequence of inputs that you're processing. And so you used a masked self-attention matrix for standard left-right language modeling or right-left language modeling, where you mask the upper triangle, and that prevents you from that future linking. And so, when we say bidirectional context, that corresponds to training the same self-attention transformer, basically, except you no longer have this masking to prevent future locations like J, after I, being able to have I look at and attend to position J after I. So that's kind of the architectural detail that corresponds to this change. And it kind of makes sense that having that ability to look at both sides of context helps with disambiguation. It helps with information processing and information flow through the model, because the model can query back, and for things like question answering, for instance, if you have the question after the context, you can't update the representations of the context in a left-right autoregressive model after you've seen the question, because they're masked and they're hidden from it. So the model isn't doing any right context dependent processing. But in BERT, it can actually bidirectionally attend and quickly pass information forward and backward. And this is just what you see. If anyone who actually does self-attention architecture from scratch on a supervised task, they always use bidirectional, or almost always, instead of masked self-attention matrices. And so this turns out to have a huge boost on glue. So that bump, I believe, between GPT-1 and BERT was they went from GPT-1 had an average of 78 or something. Or sorry, excuse me. I think this got reworked, and we excluded WNLI. It was a bump of 5+%. So it basically doubled the headroom on GPT-1. And they show with very careful controls that for the exact same model in the exact same setting, it does quite a bit better. So bidirectionality, it makes sense also for sentence comparison tasks like entailment, where you have two sentences you're comparing. You really want the model to be able to compute and tend back and forth between them, and look at one and then the other. That just seems like correct behavior to do. Whereas GPT-1 would just go left, right, and then you'd be done. So yeah, BERT ended up being kind of the thing after Elmo. So Elmo kicked it off, especially in the research side, and got a lot of people to start investing in this space. BERT is kind of the thing that moved this to the point where suddenly it was ready for more commercialization, or production ready, basically. And so this is now deployed in Google search and has really kind of shown up everywhere. If you go to basically any leaderboard, BERT variants are often very near the top now, and pretty much most NLP tasks. And just like GPT-1, they use the same architecture everywhere. They removed the need for kind of having these task-specific modules on top. And so this was another incredibly strong step. So, that was BERT. I guess there's one more point to make, which is because it's predicting these masking tokens, it's only predicting you have to set that mask percentage. And by default, it's often set to 15%. So you should understand that your left-right model, it actually predicts a lot more words because it'll predict the full sequence within a single forward pass. Whereas by default, you'd have to run a BERT model 6 times to on average predict every token. So it turns out that they often learn a bit slower early, but then they just keep training and they begin to learn how to use the bidirectional representations to their benefit. And then they continue to outperform left-right language models. Now, the problem is you can't sample from it, and it's no longer quite as clear that it's you can't compute a correctly normalized probability over the sequence without a lot of work. There's some research into figuring out how to do this with clever methods, but kind of it removes some of the elegance of sampling and having easy density or probability estimates for kind of trading off this representation capability. So Roberta is, if we go back to this leaderboard, the next big jump up from 80.5 to 88.1, and kind of as a benchmark or important event, it kind of solidly is above the supposed human average baselines here. So what is Roberta? Roberta is a very well executed engineering refinement on BERT. It's a good example of how so often in this field, kind of the second pass at an approach with maybe the same very similar model architecture algorithm can, just by careful engineering and fine tuning and tweaking, still have tons of extra headroom to it. So they better tune the hyperparameters. They remove a few hacks that the original BERT had. So for instance, the original BERT, for computational reasons, predicted most of its training on a relatively short context length of, I believe, 128 tokens. And then right at the end of training, doubled that 2 times to up to 512 tokens of prediction. And so they just train at 512 the whole way through. And it's the same model capacity. It has the same runtime per sequence length, but they just, they spend the pre-training compute to buy that. And when you're thinking about deploying the system, one of the important criteria to realize is, especially when you're talking about a system that might get deployed broadly and used across the, across the world in many different companies once it's released, most of the compute is going into inference time. It's not actually going into training time. And so that means that if you have a method of getting further performance improvements by spending more flops at pre-training time, often it can be quite worth it from like kind of a full ecosystem view of where is the compute being spent. And this is one of the counterintuitive things I think about how you think about these systems. So they also do better data generation. It turned out that the original BERT, kind of from a simplicity perspective, cached the masking. So they only actually mask the sequences once, and they always predict the same mask location. And so you could simply change that to an online setting where you keep resampling the mask, and that helps with overfitting. And they also use a more flexible vocab scheme. They use kind of a full BP scheme that can do kind of full UTF-8 byte sequences. So you can handle any string, at least with the standard byte sequence representation. And then they just train longer with more compute. So as we mentioned before, BERT is only predicting like 1 of 6 tokens on average. So that just means it's undertrained for the equivalent amount of time, and you can actually just keep training it longer with more GPUs and continue to see higher and higher performance. And so I mentioned BERT was on the leaderboards everywhere. Well, now about 8 months later, it's Roberta everywhere on the leaderboards, and that's still true today largely, except for a few like targeted things. I think if you go to the average NLP leaderboard, you're going to find that model in the first place is some variant of like a Roberta or something. So that's like an example again of where it's not like there's no super clever new algorithm or approach, or and even for BERT it's a pretty it's a pretty precise refinement of previous of like GPT-1, but it can have a huge impact when it's just well executed, and is I think somewhat exciting from one view, where it's like, okay, we're kind of really finding that there's a lot of fertile ground here, and with like kind of the right tweaks and clever insights, we can continue to make further progress. So this is where Electra comes in, and this is like I think one of the ones that first shows kind of another new interesting algorithmic potential improvement, and somewhat excitingly shows that it's much more efficient. So we mentioned the masking for BERT. So there's actually this kind of gap here, which is the problem is when you're training, you're masking all of these input sequences, and you may sample the mask rates, so you're kind of corrupting your inputs. But then when you want to train at test time or when you want to transfer to some downstream task, it doesn't make sense to corrupt the inputs, right? Because if you were doing sentiment analysis and you mask the token, this was a mask movie. You don't know if it's going to be a great movie or a terrible movie in that mask location. So BERT just kind of like has a few tricks to like minimize this impact. But at the end of the day, it's kind of this train test gap where you trained it with one distribution with mask inputs, and then you want to test it and predict with it on a different one. And then it turns out that that gap actually looks to contribute to some performance issues. The other gap is, again, it's only predicting 15% of tokens. So it may also be learning slower than it could because you would have to fprop 6 times to see predict the same amount of data. So what Electra does is a very clever hybrid system. So they have a BERT, or basically a mini BERT inside of it. So it's the standard masked language modeling technique. And then you sample from it and you say, well, for that first word that we masked, what do you think is the right word? So you sample from its distribution over next tokens. And then you're going to feed it into this discriminator, which is the actual Electra model. And what its job is to predict whether or not the token at any given location is the original token or a replaced token. So if the generator gets it wrong, again, it might sample something kind of reasonable and kind of correct, like cooked versus ate. The job of the discriminator or the Electra system is to just estimate, is this the correct one or not? So it's just a binary classification task, but it's done at every location. It's basically saying, was this input corrupted? And that allows it to, one, it has a natural distribution, and it may be, because this masked language model could be quite good, a lot closer to the real input distribution. So you don't have this shock when you transfer it for a downstream task. And you also speed things up because you're taking a loss and propagating a gradient for every location, because you're always estimating, is it the correct one or the wrong one? And that's like still can be a difficult task for every location, rather than like kind of the degenerate thing for like 80% of tokens, which is just like the identity function for BERT. And so when we look across the board here, we see that this model, kind of the standard models, and you get like Glove or Selmo versus BERT, and they're all kind of like smashed up right here on 0, and GPT-1 starts to move over, and then you get kind of Roberta, which scales with more and more compute, and then the graph keeps going and it's hidden. You can see that Electra's kind of across the board can be quite a lot more efficient, and often by like factors of 5 for kind of equivalent performance on a data set. So that's quite exciting. And in the limit, they show that, for instance, in Electra, a small Electra model, so quite a lot smaller than even a GPT-1, by exploiting bidirectionality in this dense training function, can actually outperform GPT-1 in 2 days on a single V100, whereas GPT-1 was 25 days on 8 P6000s. Partially this is because of FP16 versus FP32, but it really shows like how, I think unfortunately some people have, and it kind of makes sense because I've talked about the importance of scale and whatnot. Some people have kind of like written this whole subfield off as like whoever has the most GPUs is going to win. And oh, it's all just training bigger models, and maybe as a newer grad student or as a hobbyist, I don't have access to the resources to do interesting work in this space. But a paper like Electra is really exciting because it shows that a single commercial GPU can actually still have very interesting results in this space. Now, admittedly, they still run the best performing version of the model on a TPU pod, but here you're already having last year's model being beaten in a day or two on a single GPU next year. So I think that's a very exciting point. And this is from Clark et al. I believe this is Stanford Google collaboration. I think it's Kevin Clark. Sorry if I missed his first name. Yeah, so it's really exciting work here. And there's this final one, this is like kind of the deluxe result coming out of the space from Colin Rafal and collaborators at Google. And this is like kind of after the first crazy year of like, well, there's Bird, and now there's Roberta, and now there's all these things coming out one after the other every few months, bumping up the leaderboard. This is the paper that like took a step back and kind of more systematically studied the space, analyzed it, used a lot of compute to do it, but kind of really brought a lot of things together and kind of very carefully curated. It's a treasure trove of information for this space. It's 50 pages long. There's pages and pages of tables with hundreds of numbers in them, so it can take a while to work through it, but I really recommend it as like one of the ways to like get up to speed on this whole area and all the techniques and all the different ways. So they again systematically study this. So there's standard language modeling objectives, there's BERT style masking, there's their own kind of things like span based extensions of BERT, and then they also look at differences in the architecture. So there's your standard left-right language model. There's encoder decoders, which could have like a bidirectional encoder that processes like the previous sentence, kind of like skip thought style, and then an autoregressive decoder. And then there's a clever hybrid called a prefix LM, which is a single, well, you could have untyped weights, but you can think of it as like a partial untying of the masking in a self-attention matrix, where you allow some part of the sequence to do bidirectional attention, like in the past, and then you switch over at some point to doing autoregressive like language modeling. So you can get the benefits potentially of, for past context, doing bidirectional representations, or in the limit, if your downstream task is always just going to be bidirectional, you can just run it in purely bidirectional mode. So it's kind of training a hybrid system, and I think that was also a quite clever improvement they had. The other thing I really like about this paper is it goes even farther in terms of elegance of kind of this shared framework for doing all task and all predictions. So kind of one of the trends has been moving away from these custom architectures to kind of these shared pre-trained models that are a little bit more monolithic and can be used across a wide range of tasks with high performance. And so T5, typically like, with GPT-1 and BERT, the only difference we would do is we'd still slot in the linear classifier at the end to like predict which of the right classes is correct. So what T5 says instead is, and this is actually something that Brian McCann and collaborators at Salesforce introduced about 2 years ago, is they basically say, we're going to phrase everything as like pure natural language, pure question answering or something. So we're going to give the model a command or a prompt as the prefix, like translate an English sentence to German, and then it'll give it the English sentence that is good. And then T5 just through natural language routes that to, das ist good, or something. And for all of these, it does this basically. So for the COLA sentences, it'll predict the language phrase not acceptable. And for STS-B, here's a kind of almost silly version where it's a continuous valued sentence similarity prediction task. And then they just have it output discrete token 3.8. So it has to, but because it's pre-trained, it's learned kind of the continuum of numbers and the similarities between them. But it's kind of hilarious for me to see a regression task reframed as discrete token prediction. And again, it's quite general. You can do summarize and everything. And so we saw a little bit of this with like when we were probing with like Roy Schwartz's work, just using natural language and like probabilities from the language model, or like some of those zero-shot transfer experiments from like GPT-1. And so like T5 really goes through and shows, yeah, you can actually exploit the natural language that it's learned, and that helps with the transfer and helps with the fine-tuning task potentially. So yeah, T5 is a really good kind of overview of like all the work in the space, and then they also just threw a big model on it too at the end, and yeah, that gets you another bump on those leaderboards that we were talking about. So that's that in fourth place though now, so others have done some more things on top of it. So that's kind of, I think, the core like set of literature I wanted to cover here and ideas. At this point, we've kind of gone through the history of kind of language models and how they've been adapted and used across kind of you know, the winding history here of how kind of NLP like kind of really took off with these unsupervised and self-supervised methods, and kind of figured out how to use them in all these different papers that kind of found pieces of the puzzle and proposed different methods that did or didn't work, and kind of combined well with other, you know, modeling improvements and everything. I think it's a really cool story. I'm excited that I was able to chat through that with y'all today. The last bit here now, we still have about 15 minutes left, but we should maybe leave a little bit for questions at the end too, is kind of just a bit of more high level thoughts on, this is an unsupervised learning course. Why do we need it? You know, what's wrong with the current paradigm of supervised learning? And I'm sure you see motivation, you know, and there's been great discussion already on this topic here, but kind of I would like to share a bit of my own like thoughts and opinions here. So, you know, I think a motivating thing here again, kind of we've had this thread running through a lot of the discussion so far in this talk has been, how well does supervised learning work, and, you know, what should we expect of it? And so kind of concurrent with some of this stuff taking off in the last few years was kind of a lot of work that started critically evaluating kind of deep learning for supervised NLP. So, you know, for natural image inference, for instance, this is a three-way classification task. And even before pre-training really took off, so eSIM is using just word vectors, and it was a very, you know, well-designed architecture. They nominally got to, you know, average human accuracy of I believe a single Turk worker. It may have been an ensemble of 3. So it's like, whoa, is this done? Did we already hit human accuracy? And, you know, like, I think everyone kind of knew, well, no, because clearly these models are, you know, still making weird mistakes. And this is kind of where in the last few years, there's been a lot of great work starting to really quantify these concepts of how robust are models, how well do they work out of distribution, kind of pressuring and challenging the standard supervised learning paradigm of, you know, training on an IID training set and evaluating on another IID split of held out data, and basically showing that that's no longer sufficient and something's going wrong somewhere in supervised learning. That means this is a being too fortunate to our algorithms and you know, not being fortunate enough to humans. And so this is a great paper from Suchin, I believe, called Annotation Artifacts in Natural Language Inference Data. And so when you do hear people talking about, oh, these models are exploiting statistical artifacts and biases of the training distribution, you know, this is a paper that really nailed that down and showed it quite conclusively. So, you know, they kind of start from a high level of, well, how were these data sets created, these supervised data sets? You know, admittedly, they're kind of artificial. You're paying people to label these tasks. They're not natural instances of the task. They're kind of what people can come up with on the top of their head, or, you know, they can have very good experimental methodology. And data sets like SNLI and multi-NLI are some of the best we've got in terms of like very good setups, you know, curated by people who really know what they're doing. But you still run into the issue of like, well, you've got to have a human generated example, and, you know, maybe they're less creative than you'd think. So the data is actually drawn from a much more narrow distribution than it should be. And so this paper kind of went through critically and showed a lot of these artifacts actually showing up. So, you know, a worker would be told to make a, you know, a negative or a contradictory label. And so they would just be like, oh, I'll just slap a not on top of I'll copy the sentence. You know, and it's not quite this bad, but it gives you the idea of what's going on, is they'll copy the premise sentence as the hypothesis, and they'll just put a not in it. Or they'll, you know, to have entailment, they'll just restate the sentence in a more generic or abstract way. And so you might go from, a dog is, you know, playing to an animal is playing, or a pet is playing, or stuff like that. Or you'll add some kind of like superfluous information, like tall or sad or popular, to hint at the neutral class, which is like, well, it might be true or it might not, but it's not clear either way. And so what they showed is, somewhat disturbingly, if you only trained a model on the hypothesis sentence, so the second sentence, and again, semantically, this task is defined as the logical relation between two sentences. But if you trained a model only on the second sentence to predict which of the classes it would be, it actually did, it basically got half of them right. You know, it went from 33 to 66%, or so it was a large bump. And, you know, by default, we know that model can't be doing the true task because it's just predicting, you know, given only the random second sentence. So this is a great example of where you can see that standard supervised learning might be picking up on these spurious correlations or artifacts. And, you know, eSIM, when you evaluate it on a new hard set, which is the set of answers that the model that only looks at the sentence can't get right, drops quickly from like 16 percentage points, from 88 to 72%. And this shows up across the board. There's now probably a dozen papers in this space, if not more, that show that kind of these NLI systems that, you know, nominally we're supposed to have human level accuracy actually are not consistent or not robust or not systematically generalizing. So, you know, this is another one from Glockner that, you know, very carefully constructs kind of these probe sets of like permuting objects in the sentences or permuting, you know, synonyms or antonyms. And, you know, on these probes, they show that, you know, accuracy again drops quite a lot. And then a final point here is on distributional robustness. So this is a paper from DeepMind called Learning and Evaluating General Linguistic Intelligence. And so what they showed is those near SOTA question answering models, which again on Squad, it's you take a Wikipedia sentence and you take BERT, which we've already talked about how much of an improvement it's had and, you know, how you know, it's improved scores a ton. So you take that sentence, that question answering model that's trained on Wikipedia, and you just run it on a different data set. So still question answering, except maybe we run it on like trivia factoids that are sourced from like Google search results, or maybe we run it in a more conversational framework with kind of, you know, two people asking questions between each other. And we see that just like accuracies can crater, or, you know, F1 is basically an accuracy metric here. So it's, you know, the same task. And we know that people, when you ask them a question on one task versus on another, they're going to do about the same. You know, maybe, yes, one task is a little bit harder than the other, but you don't see them like suddenly, you know, lose half their accuracy. So this again just hits at some of the distributional robustness issues and brittleness we're seeing. And again, this is still some of the best stuff we've got. It's combining supervised learning and unsupervised learning, but there's hints as we're going to go through here that these self-supervised methods and unsupervised pre-training is really helping with the robustness. We're still not there yet, but we're making progress, and a lot of that's being driven by moving away from a purely supervised learning framework to moving to these like hybrid and joint training and pre-training methods. So as I mentioned, like there's a lot of things that could be going on. Current techniques are brittle, they're memorizing instead of generalizing, they're explaining spurious correlations. They, you know, also stop learning. Once you get to, you know, memorizing your training set, the model turns off because the gradient dies and training loss goes to zero. So it just kind of feels incorrect. So there's like a lot of different routes we could go down to make progress. We could do better models and architectures, we could do more data, we could go down different paths altogether. So obviously, since I'm kind of talking about unsupervised learning, in a supervised learning class, I'm going to talk about how that's the very exciting one. But, you know, we could always keep working in the supervised learning paradigm and just say, well, we're going to have better models and we're going to get more data. We're still going to kind of approach this problem from the same way. And so this was like kind of what I'd say a lot of like early deep learning was really highlighting, was kind of, you know, we were working on supervised learning data sets, and we kind of were seeing, you know, these new architectures that were exploiting priors and inductive biases of the, you know, data domain were really helping a ton. So on images, you know, this is the grand story of we added, you know, COMNETs in, and they are a great fit for the domain, and they kind of cleverly encode, you know, all these, you know, equivariance and translation and, you know, shared weights and all this structure, and that helps a ton with their accuracies. And then we would just use a large supervised data set and let HGD figure it all out for us. And so this kind of led to, I think, a mindset of heavily emphasizing architecture engineering. You know, there's a very large design space here. Somewhat cynically, it allows for a lot of different papers to be written. And, you know, you can really kind of combine and contrast like all these building blocks. Like we really like playing with these blocks, and, you know, a lot of really good work has been done that like does empirically push the state of the art by exploiting, you know, properties of domains. And, you know, an example of that is this diagram on the left. So does anyone want to guess the name of this model? Well, sorry, because it's kind of hypothetical. It's called a simple model. So this has got 6 different color embeddings, and, you know, there's GRUs and character models and biattensions and MLPs, and you know, it starts to get quite complex when you're really all you've got is inductive biases and kind of the standard supervised learning data sets. So it's a heroic effort, but you're kind of exploiting more and more details and getting more and more complex to make progress when you kind of have locked in these other constraints like the data set size and, you know, the paradigm of training. And on the right is another one that I think is like almost looks like it's like some like pentagram or something. They look like kind of these very cool like architectures, and they're very quite fun to look at and kind of look through all the work that's been done on creating these systems. And again, like we said, there's all these different methods of adding inductive bias, and it can really help a lot. And so they're all important and very impactful. And please don't take this as like criticizing kind of the standard approach of like iterating and hill climbing on supervised learning with like better and better architectures. But I think it's a bit like this, where really when you treat a data set in isolation, if we come back to how people learn and experience the world, it's so varied, it's so diverse. There's so much experience and information and knowledge you're leveraging before you ever saw this data set. And so machine learning models, when they're started in isolation on a supervised learning data set by itself, are kind of like, that supervised data set is like a peak in a very big space. It's a small peak, and we can add more and more data and make that peak more, taller and wider, and that might help with robustness and generalization. But at the end of the day, it's kind of a little bit futile, I think. The real way to solve these tasks, or at least the way that people do it, is they don't sit down and memorize, a million different examples. They somehow learn a much more general set of task behavior and transfer of knowledge and information, instead of like just becoming a master at a very specific isolated domain. We're amazing because of our generality, not because of our, we're amazing for both because we can do incredible things in specific domains. But at least machine learning is starting to see that on very targeted supervised data sets, you can get models that do a bit better. And so then there's papers that even on architecture engineering show kind of somewhat critically that some of these, fancier new architectures, at least some of them, don't quite improve as much as you'd think, or with more careful ablations, don't show much of a benefit. So, there's one of the famous examples here is they took a baseline LSTM and gave it some love. This is kind of a common story for language modeling, and showed that it was outperforming kind of a lot of new recent state-of-the-art models if you just had careful comparisons and careful fine-tuning. So, maybe we need to back off and rethink beyond just pure supervised learning on task-specific data sets. And I think one of the reasons to frame this is the largest supervised data set, basically in the world that I'm aware of publicly is GFT 300 million. Actually, never mind, there's a Facebook one that I haven't talked about, their Instagram pre-training. But this was true a little while ago. So this is 300 million images, 18,000 classes. If you do like a very simple, like loose bound on how much information content you get, you have like log 18,000 bits per image, and you have 300 million of them. So that ends up with about getting 350 megabytes of constraint on the function you can learn. So this is the world's biggest data set. And in terms of the correct function that we're trying to approximate with supervised learning, we only are able to pump about, from this kind of slightly naive and toyish view, about 530 megabytes of information into the system from the supervision here. But, like trying to connect this back to everything we've been talking about today, there's, terabytes and petabytes of actual raw natural language on the internet. So if we figure out how to exploit all that information in some reasonable way, there's a hell of a lot more there that we should hopefully, and again, we're going to be a lot less efficient. Gold labeled supervised data, per bit is probably helping far more to specify and learn a task, but we only have a little bit of it. It's like, Jan's cake analogy of the cherry on top versus kind of, everything else we need to be able to do. And I kind of tried to take the supervised learning approach for language for a while. I spent most of 2015 myself building what I hoped would be an ImageNet for text. It was a very large weekly supervised data set where we basically did classification over Reddit communities. And we built like 150 million training examples over 1,000 communities. We trained RNNs to predict everything, and we're hoping they would learn useful features and representations, kind of skip thought style. It was pretty concurrent work at the time, except we were going with the supervised route instead of the unsupervised route. And the sad thing was the unsupervised model beat us. So skip thought vectors was beating, just by doing a language modeling objective, was beating this system that we built with like, admittedly weekly supervised data, but we were like, oh yeah, this is the gold labels. These are the right things to predict. They're semantically aligned with classification. And then this kind of really made me quite confused and kind of skeptical of some of what's going on in the space because, or at least of supervised learning, and got me really excited more on the generative learning and supervised learning side, because we just weren't seeing the supervised learning pull through here, because it just, I think, is a little bit too weak of a supervision source and a little bit too specific. So like, again, the big question I think is a lot more, in terms of like novel research frontiers. How do we go from kind of isolated peaks of competency that you can very quickly, fall down if you change the problem just a little bit, quickly collapse in terms of task mastery? How do we go to systems that perform, in a much more general, robust kind of, maybe they're not nearly as good in terms of competency on any given specific task, but how do they perform much more broadly across the board? And again, so this is an example of kind of the classic architecture engineered approach, like one of the kind of incredibly well done versions here that's exploiting so much information with inductive biases. It's using WordNet, which is like that great hand curated data set, and so we see that it like gets and because it's able to exploit all this site information of helping with like learning, oh, these are synonyms or antonyms, or this is more abstract or less abstract, a child or a parent in terms of like semantic hierarchy of a different word. So you can see how that's bringing in the information that should help with generalization. And so it actually does better on those kind of systematic evals. So this is one way of like widening that peak. And somewhat excitingly though, if we just slot GPT-1 in as well, it performs just as well on the more robust transfer setting. So there we didn't have to manually curate that the relations between words or build WordNet. We kind of let a language model figure it out. And so I think this really, again, is one of the proof points that, this unsupervised pre-training is really figuring out the same relations, the same kind of connecting the concepts, connecting them, and helping with robustness and generalization. And there's some new work from Dan Hendricks this week that unfortunately I haven't put in these slides, showing that BERT-based models are much more robust out of distribution than classic purely supervised trained models with like LSTMs or CNNs. So I think that that's starting to get much more well empirically founded than kind of me spouting off one or two numbers from like the models I know. So kind of at the high level takeaway here, kind of this is just a hurrah message for everyone taking this course, is, I really think that one of the most promising methods of moving forward here is in terms of like really learning tasks and robust systems that actually, perform the things we want them to, is we need to move away from standard supervised learning. Instead of manually specifying what to predict through the creation of large supervised data sets, we need to figure out how to learn from and predict everything out there. And one of the ways that you can think of this is like every time we build a data set, we're setting the importance of everything in that data set to 1, and everything else in the world, all the other useful information maybe out there, is set to 0. So like when you start with a model from scratch, you should really get in that supervised learning model's head and be like, oh, it's almost a hopeless task. They know so little, and we've hidden so much from them when we only give them this one canonical gold standard data set. And of course, they're going to cheat however they can because they're great at optimizing the objectives we give them. But if they don't have the foundations with which to truly build off of, all they can do is exploit clever spurious correlations. So yeah, I think this kind of comes together with all the work we've been chatting about of like a potential recipe for, and I think this is getting proved out with T5 and all of the future work here of how to kind of combine a bunch of pieces together. We need high capacity and flexible model classes so they can handle a lot of different tasks. We need algorithms for extracting information and learning the structure across many different domains. So this would be basically, a lot of things we talked about. It turned out language modeling actually just worked really well as one of these. It's an incredibly old idea, but that algorithm just, or method just worked quite well in terms of people. There's a lot of different clever approaches to specifying proxy tasks, but this simple one has gotten us quite far. And you're unfortunately still going to need, because these are dumb models that don't have anywhere near the robustness or generality of humans, you're going to need a lot of data tiling everything, but at least it'll be unsupervised, and so we have it available. And you're going to need, unfortunately, at least to get the the soda grind on the leaderboard, an offensive amount of compute with which to learn them. But again, that may produce a model that's actually quite small and efficient to run at test time. And I think that's one of the hopeful directions going forward, is you train these big models, and Google or Facebook or OpenAI burns the GPU years to get that model. But then you're able to distill it and prune it and release it, and then it can still run on your own laptop or on a single GPU. And that means that those downstream tasks that you may want to investigate or build models on are much more efficient, because you've amortized all this compute that went into pre-training, and now you're able to use that during fine-tuning. So it may actually be that like BERT is actually, though it took a ton of compute to train BERT and Roberta, may actually have reduced the overall volume of compute needed to achieve a given level of result, and may actually widen the amount of usefulness and tasks that can be tackled in the field, because it can transfer and be beneficial to everything downstream. And I think it's very reasonable that some people in the field kind of look at all this coming together and are like, well, I don't find that satisfying. And so I think that's a valid view. And so, maybe backing up and working towards, more grounded learning. And there's lots of really interesting work in this space now of, moving towards reinforcement learning and grounded learning with, multimodal agents and all this kind of stuff that connects to, more what feels like, true learning about the world instead of just seeing abstract bits of text. I think that's a very valid approach. But right now, we've been just seeing that it's been driving a good chunk of empirical progress over the last few years. There's a whole other set of methods here that's multitask learning. And I think that's actually been showing a lot of promise in the last, when I made this slide last year. I think I was a little bit more pessimistic on it, and there's actually been a lot of good work like MTDNN and others that's been making progress on this set of methods. But it still kind of relies on us building a data set. So for multitask learning, you train on a bunch of different tasks together, and you kind of hope that you get transfer naturally between them. But often they're all supervised tasks. And T5 is a good paper to actually like really talk through the nuances of multitask learning versus generative pre-training. And one of the surprising things they show now is when you do it well, and you kind of exactly emulate the pre-train and fine-tune framework. If you do multitask pre-training followed by supervised fine-tuning, you still need the unsupervised objective of like masked language modeling and the like. But you can get rid of, or you can at least find very similar performance in many cases compared to having to do the giant pre-training on the full internet, for instance. So there's still headroom left in potentially improving these methods. And the final one here to just chat a little bit about is some of the follow-up work we did at OpenAI on GPT-2. And this is kind of like what I've been chatting through here is kind of like a lot of the motivation that went into this project. So we collected more data compared to GPT-1, and we collected much more diverse and heterogeneous data. So we're hoping that we'd have models that would generalize better and see a much broader set of tasks. So it's 40 gigabytes of text, 10 billion tokens, 8 million web pages. We scaled up the models just because we kind of saw those trend lines, and I think there's a lot of reasonable arguments for why you just need bigger models to handle complex tasks. And it's just a language model, which predicts everything. So admittedly, it's a left-right autoregressive model, so it has some drawbacks compared to things like BERT. But it's just a language model. And so what we focused on in this case was purely how well this model could do across many different tasks in a zero-shot setting. So we never fine tune it because supervised learning is tricky and it learns to exploit spurious correlations and dependencies. So we're only ever saying, well, you did all your pre-training work and we had you predict a bunch of words. How well can you handle this new data distribution you've nominally never seen before? Admittedly, we train on a lot of data, so we actually see a lot of data distributions. We're not letting it like specifically train for that specific task and with that specific label. We're just saying run it and see what it can do. And we show that like it actually begins to do something, particularly as you scale the model across a wide range of canonical NLP tasks. So it's purely unsupervised. There's no direct human labeling or supervision going on here. But this model can actually, you can feed it a paragraph and then ask a question, and you get transfer. And the language model can give you the right answer sometimes. Often they're just matching kind of old baselines, and they still have a huge gap to the human performance. But I feel like this is a much better measure of potentially what the like underlying performance of these systems might be, because we're not doing supervised training here. And unsurprisingly, we know our models are still worse than people, so that kind of shows up here. But it also shows a promising trend line where in some cases, like there's very domain-specific algorithms for unsupervised translation. Admittedly, it's been a year, so this peak should be up here now because there's like some great follow-up work from Fair and others pushing unsupervised NLP farther. But this is just a language model with no real customization, and we're just seeing that it begins to do translation between like English and French. You can tack a TLDR on the end of a document and get something like summarization. It's pretty garbage on the official metrics because it's only barely matching 3 random sentences from the article. But kind of quantitatively and qualitatively, if you ask people which you prefer, it looks a lot better than these numbers show, because this is a kind of very coarse evaluation metric. And then the final thing here is like question answering. So this kind of shows domain knowledge and kind of world knowledge and potentially a lot of factoid information. And this one, we unsurprisingly see a really strong scaling curve with model capacity. So like, how is this working? How does this kind of unsupervised system, it's just a language model, begin to do translation, question answering, and reading comprehension? Well, if we go through and inspect our data set, it turns out there's actually just like kind of natural occurrences of tasks. And you're training a model to predict the next word, so it has to, it sees an English sentence, and then you're like, and then it happens to just have, inside of the middle of this article that someone wrote, a training example of English to French. So it's a much more natural way of learning. And when you have very large data sets, you just actually begin to have a non-trivial amount of that data. And so you see for translation, for summarization, like if we just like grep through the data set, how many times does TLDR appear? Well, there's 100,000 training examples in quotes here. And how many times does like someone ask a who, what, where, when, how, why question? Well, there's 6 million of those. So we're kind of seeing that these kind of systems that, you know, don't make assumptions necessarily about any specific task, but kind of try to predict everything, kind of really begin to make some progress. And again, like one of those areas we saw the most on is this question answering and open domain question answering, where you're just asking like, what is the capital of, you know, Paris, or in what year was Star Wars released? And, you know, I think that this kind of gives you a very clear picture of why supervised learning with like kind of the standard approach just is never going to really be able to solve this kind of task. So on the x-axis, we have number of training examples seen. And again, this is log scale. And yeah, if you start with a randomly initializable model, there's no way it's going to be able to do question answering on an open domain. You know, there's no way it can have the information for, you know, what is the capital of Paris until it's seen that training example. And there's very little generalization there. You just need so much data to approach this from a naive supervised learning approach. Whereas as we have bigger models that have more capacity, you know, in the limit, they very quickly begin to do non-trivially on these data sets. And then they kind of fine tune in and learn how to better extract the information that's somehow contained within the weights to various degrees. So again, this red baseline here is completely randomly emitted. And these are basically random guessing numbers the entire way through. Even though this data set still has 20,000 labeled examples. But as we try bigger and bigger language models, we see that they really begin to make progress on this. And T5, I think, has continued pushing this quite a lot farther to where they're actually sometimes matching with only a neural model that's never looking at documents with like the actual factoids in them. It just from its parameters is able to answer quite competitively on some of these tasks. Yeah, we're pretty much into conversational period at this point, but you know, some of the takeaways I would kind of say from this, and kind of, you know, really pushing language models for a few years here is performance is, you know, not usually limited by something single paper fixes. This is a very long history of, you know, I think we probably talked about 25 papers during this trajectory of research here. And usually it's always someone chipping away on one specific axis. You know, diminishing returns basically mean there's always some other bottleneck. So if you scale the compute but not the data, you get bottleneck there. If you scale, you know, the parameter size, you'll just need more compute. Or if you scale, you know, the model capacity but don't increase the data set, it'll just overfit. Or you could try to scale via like, you know, human intuition, and you could use fancier models, but maybe that's just more difficult to train. So kind of, I'd say that, like, you know, particularly if you have a little bit more of an engineering mindset here, kind of the pragmatic approach of kind of pushing on all these axes together may allow kind of for a larger effect size to show up than pushing on any one in isolation. This is an unfortunate tension, I think, in research and science, where you often want to, you know, microscopically measure effect sizes of well-controlled ablations and experiments in isolation. But, you know, if you change a few things together, you might actually see more of an outsized effect. And so that's like one of the things we did with GPT-2, where we get more data, get more, you know, bigger model, throw everything kind of together, and try to see if that really pushes toward qualitatively different behavior, maybe. Yeah, I mean, I really could transition into question period at any point now. You know, there's a little bit more advice at the end, just saying that don't work on large scale models, particularly, you know, like as things like Electra show, you can work on the smaller models and see the same effects showing up. They're not going to have the same accuracy curves, but, you know, we know from scaling laws and kind of all those trend lines that if you start seeing an effect that's robust at small scale, probably fingers crossed it'll also hold at larger scale. So you can do a lot more rapid development, and you know, and this I think works quite well. You know, you should try 10 times as many models that are just 10 times smaller each, and you know, that way you can run 10 times as many experiments in parallel. You know, this is still you know, a large research field, so there's a lot of things you got to try. And you know, all the behaviors in a paper like GPT-2, which kind of I feel like gets pointed to as a canonical like big compute, big data kind of thing, they still show up on models you can train on a single desktop. You know, it takes a week to see the hints of that, admittedly, but you know, GPT is small. You can train quite well in about a week on like a 4 GPU setup. And then after you get your proofs of concept on like your algorithm or your idea, then you can scale up if you can have the compute resources or get a you know, a loan of time on a cluster or things. And kind of the same strategy used back in the day with like the sentiment unit, where the initial proofs of concept were 512 dimensional STMs that took a day or two on standard hardware. And then, you know, for the final version, then we kicked off a big run with a model that took 16 times the compute. And how do you not go insane when you wait for a model to train for a month? Well, we like to do this thing at OpenAI where you boot your big model right before you go on vacation. So you boot that before winter break, and you just let it train over the break. And luckily, fortunately, you're able to set aside a machine for the whole time. But don't stare at that graph every day. You won't make nearly as much progress if you're just staring every day at that number. But often models surprise you when you give them more time to learn. So when you're really trying to push that result at the end, it's a really good idea to try that if it's available and an option. Yeah, and again, one of the other surprising things just about this field has been how far we've gotten, pushing often where the developers of one paper or model or architecture only just pushed on log probability or the type 1 evals, and then someone else coming along in another paper and showed, oh, this thing's actually great at type 2 evals. So I think that's really reassuring. And I'd often say that you could work on one or the other in isolation, and often you see things that robustly scale on both or contribute on both sides. There's some gotchas always with scaling. Things break when at some point you can't extrapolate too far, and things just change. So you've got to watch out a bit for that. For like a model like GPT-2, Riwan, one of my collaborators, was like, we were originally trying to train these deeper, bigger models, and they just weren't working better. And we had to fix an initialization technique, and Riwan came up with this, and it helped continue scaling. So when you see your scaling like not happening the way you'd expect, or the trend lines kind of suggest, it's often a sign that something's wrong and you need to like tweak it or fine tune it, or come up with like actually do the clever work. I don't do much of that myself, to fix it up and try to keep making progress. Yeah, and then the other thing is just like writing efficient and smart code these days. Luckily, hardware is improving, and for the same price point. So with things like FP16, half precision compute, if you switch over to that with things like, with an example being GPT-1, the original version took 25 days in FP32 and 1 generation older hardware. And then the same next generation hardware where a lot of people did a great job optimizing this. So Scott Gray in particular is an amazing GPU engineer and researcher at OpenAI. He worked with us on the BlockSparse, or the BlockSparse work is basically his work. And he was able to optimize these down by almost an order of magnitude on just the next generation's hardware, from a lot of great improvements across the field. So often if you write efficient code, and use all the right tricks in terms of accelerating your models, you can wring a lot out of the same level of hardware, and just be efficient about that. We have a library called the BlockSparse library that can help with that and provides a lot of these ops. And honestly, also libraries like PyTorch now are doing a great job merging these in, providing their own ops kind of more integrated into these instead of these kind of wrappers. So that's, I think, exciting for the field as a whole. Yeah, in terms of sweet spots for compute, 428 Ti desktops still can do a lot in this space. They just cost a fair amount of money. And then your standard AV100 box on a cloud provider is a medium scale compute platform. Papers like Electra can do a lot with just a single V100, and a 28 Ti is basically the cheap V100 for 4 or 5 times less. Yeah, that's about it, honestly. I think we have about 15 minutes left for questions, and I have a few more random slides if we want.
This is really great, Alec. Thank you so much. Let's see if people have some questions.
Hey, Alec, Arvind here.
Hey.
Yeah, I have a question. So I was wondering if you could give your views on, like, what do you see zero-shot language modeling as something that could be production quality performance over time, or do you think it's always going to be lower than collecting a supervised data set and fine-tuning from a pre-trained model? Just trying to understand like the space between GPT and like BERT-like models.
Yeah.
Yeah.
Oh yeah. So right now it is absolutely garbage from a production perspective with like GPT-2. I mean, well, okay. There's hints of life there. For reading comprehension, it's matching some of the original neural supervised baselines. So I'd say there's hints of life there. We're still talking about needing to do a lot more research. And if you looked at kind of the scaling laws for like what kind of GPT-2 looked like if you draw those out, there's still quite a lot of order of magnitudes left to go. So from a pragmatic or practical perspective, it's not really there right now. And that might be the scary answer, which is our models do rely on exploiting and I don't want to overhype this view, but like it may just be to actually do these tasks correctly, you do just need much more compute and something like the zero shot setting. So it's kind of like working. I think I see it kind of as like working with like lead in shoes or something, or like resistance training. I think it's a fascinating research area to push on because it does have some of these exciting qualities from like maybe representing a much more difficult and hopefully much more true representation of task performance. But yeah, it still has a long way to go. So I think it's a fascinating research direction, but there's a lot of pushing to be done on that.
Thank you.
And yeah, I think from a pragmatic perspective, like you said, you really should fine tune on some supervised data. And like I mentioned, BERT models are still showing quite good robustness out of distribution. I don't think there's been any good work comparing pure zero shot to learning of a task to like supervised fine tuning of a pre-trained model. But yeah, I think we're talking about something that's like a few years out at least.
Thank you. Thank you.
So I saw a question here. Earlier, you motivated LMs by comparing probabilities of pairs of strings to exact knowledge, such as CatSat versus CatSats. Has this intuition, comparing sentences, so I guess with exact knowledge, been used for training generative models of text, or is maximum likelihood ubiquitous? So maybe this is about a comparative or contrastive method for training generative models, where you compare sentences and know that like one should have higher probability than the other. There was one paper from a representation learning perspective, which it's not quite the generative model side, but it's representation learning. CPC, that whole family of contrastive methods is dominating, unsupervised learning for image representations. So it's somewhat of a contrast where in NLP, we haven't seen it really tick off yet. So I think it's a very exciting research direction. And the original CPC paper actually had some results that were promising on natural language, but they, like the original CPC paper in general, were exciting, but nowhere near state of the art. And a lot of the refinements in the last year or two on the image side have really pushed that quite far. I think you might have had a lecture just on that or about to. So it'd be very cool to see if someone could do that kind of similarly for natural language. But if it was about kind of exploiting more structured knowledge about like differences and encoding that into the generative model, there is some pretty interesting work on this, particularly from some more of the like linguistic heavy folks in the field of combining kind of hybrid systems of neural LLM with like kind of something like grammar constraints or the like. And it's I'd say it's primarily focused a little bit more on the settings where you might expect encoding that inductive bias to help, which is like smaller data sets. But at least personally, my I find some degree of, at least from a pragmatic perspective, a lot of current language modeling benchmarks I think are quite artificial because they work with such small amounts of data, which from a pragmatic perspective just doesn't make sense because there's all of Wikipedia out there. It's so easy to just write a scraper yourself or download a shard of Common Crawl, and that's more data than you basically are ever going to need to work with or be able to process. And so I think, at least from a pragmatic perspective, we should really be figuring out how to use the large volumes of data we have. I think it's a very valid other approach to push on data in isolation and how much how data efficient we can get with a limited set of data. But I think it's probably at just too far of an extreme when you have only 1 million words of training data and things like Pentree Bank.
So Alec, a follow-up question on that. It seems like one way to learn language is read the entire internet, right? Mm-hmm. Another way to learn language is the way I think most people learn language, which is
absolutely.
You kind of, I don't know how many words or how large a data set would be that somebody encounters by the time maybe they're 6 years old and they can speak pretty well maybe at that point. Mm-hmm. Do you have any notion of kind of how much data is required in that context compared to how much data is required here?
Oh, it's awful, at least for for neural models. I think it's for like a 6-year-old child, I think it's maybe I just bashed on 1 million words being unrealistic, but I think it's about 1 to 10 million. Compared to GPT-2 being 10 billion tokens, there's 3 orders of magnitude at least of headroom there potentially. And I think that, again, understandably motivates why a lot of people do work on that setting. But my guess would be that to really make progress in that setting, a lot of that is because of transfer between modalities and, actually, interacting with very high quality sources of supervision like other people and, being a grounded agent that interacts with, video and audio. And like, I think that research is very interesting longer term. And we're probably going to saturate kind of what we can do with these ungrounded giant systems in the next few years, or maybe it's even already starting in the last year. So that's like a very, I think, exciting next line of work. And clearly, like the numbers just show, there's a huge amount of room to go.
Got it. Thank you.
Do the techniques that work well for language modeling apply to like other modalities like videos or genetic data or something like that?
Yeah, so genetic data is actually a great example. There's a really, I think, Joshua Meyer and collaborators between, I think, was it Broad and it's an NYU team / Fair. I think Rob Fergus is now working a lot on this. So they took BERT and they applied it to protein sequences, or I think, sorry, amino acid sequences. I don't have a strong bio background, but much of any of bio background, but they were showing that the same methods were, learning like a lot of the structure in those different domains. So like kind of the sentiment unit analysis, or the sentiment unit example I gave for pure language. There was also another paper from, I believe, the Church lab at Harvard, where they took like literally my code and ran it over amino acid sequences, and we're showing that there was like, instead of a sentiment unit, there was like a beta sheet unit, or so corresponding to like secondary or tertiary structure of proteins. The models were having units that were like understanding, or even though these are like very non-parametric kind of abstract models that just like, have a bunch of parameters that just factorize a probability distribution, they're somehow learning the structure of the domain or hints of that. So I think that's very exciting, and that's another line of work. I think given how exciting this stuff has been for NLP and how much of an impact it's made over the last few years, whether it could work in other domains would be quite interesting. There's definitely differences. So for video, I think video just needs so much compute that it's like still maybe quite a few years off, just because of the volume of data and the amount of compute that might be necessary. But maybe I'm just being cynical there. Whereas on images, there's a weird contrast, which is, like I mentioned, the contrastive methods are doing quite well. And if you just run a generative model, actually, okay, that's not quite right. There's one paper from DeepMind called Big BiGAN, where they took a GAN, admittedly, pretty different generative model. And they were showing that those are starting to learn quite good representations of images, at least from the standards of unsupervised learning. Still being crushed by the latest MoCos or SimClears, but they're quite promising, and showing a kind of a foothold of this generative model kind of approach in other domains. It may be, one more piece of context to shine on there. I think there's somewhat of a nicety to language, which is because it's produced by people, it kind of is naturally designed to be very clean and very high level, and it removes all the noise. So when I think we run and try to train the same generative models or approaches in domains like images or video, it may just be that like when you're dealing with raw natural audio signals, not raw natural signals, they have so much noise that like particularly a likelihood-based generative model is just like spending so much effort and capacity trying to predict all that noise, and this noise to signal ratio is just a lot lower, that just like makes it a much more difficult task right now. I think it's a very interesting research question.
So
Cool.
Alec, we're about out of time here. Do you have any closing thoughts, or just wrap it up?
We're mostly there. I guess, one thing again is like, one of the things that I really enjoyed about being able to have the opportunity to give this talk was kind of going through and showing that full history here, and kind of, I think it's a great example of how there's so many pieces that built on top of each other. And there's so many different authors and so many different institutions that really contributed to this. And even at OpenAI, there's been a lot of collaborators that have helped push on this stuff over the last few years. And it really, you see it just involve like so many different pieces of the research, with all the different things being brought to bear, new models, new data sets, new approaches. So I think it's a really great and exciting example of like a very rapidly evolving research field that has managed to do some exciting things in the last little bit. Yeah.
Well, thank you. Fantastic lecture. Thank you, Alec. We'll stop the recording here and
Yeah, unsupervised
start
learning looks
disconnecting.
bright. Future is great. I hope continue pushing, everyone.